Welcome everyone to day 3. We appreciate your spending time with us exploring how to use the AMD GPUs for AI workloads. Day 3, we are trying to do AI, have our presentations all addressing AI for science. This is a really important thing to get across, is what kinds of workloads that our HPC centers might be doing with AI on these GPUs. There's a broad number of different topics that people can be doing in science and using the AI technology. So it's just a sampling of the different approaches and different problems. And so I think we start out today with PyTorch optimization with LLMs and Giacomo Capodaglio. So Giacomo, you want to go ahead and start and share your screen, and we will be uploading the PDFs here shortly. I think we've taken care of most of the access issues to the AMD Accelerator Cloud, and we are waiting until the end of the workshop to add the late registrations, just because we need to focus on getting the presentations done right now. So, Giacomo, you find a presentation?
I'm ready.
Here?
I'm ready to share my screen. Yeah.
Okay.
Thanks a lot, Bob, for the introduction and for kicking this off. Yet again, day 3. Okay, so this presentation here is gonna be something I'm excited about, not just because of the content, but this is actually the work that an intern has performed while working with me, Bob, and Noah Wolf from our team. The intern's name is Kevin Bueller. He was at CU Boulder at the time, and now he's pursuing a master's program at Oxford University in the UK. And it was great working with Kevin. He's done a lot of good work, and I'm gonna be the one presenting what he's done. And I just wanted to say that internships are a great way to get acquainted with what we do at AMD. We normally have quite a few opportunities in our team. So if anyone or even you is interested in getting involved with that, would be happy to engage with you. Okay, so in this presentation, I'll show you what Kevin has done to accelerate a model that does inference with LLMs, basically leveraging HIP in some Python code and also some CUDA code that was present in this model. Okay, so I'll go through the background information, introduction and motivation, and then we'll dive deep on the details about what he's done, how he's used the LLMs, some of the many versions of the different kernels that he's worked on, and then we'll show you some performance numbers on what he's done. Okay, so the goal, as I said, is pretty simple. We have a model that is using PyTorch, and we want to use an LLM to improve the performance of this model by leveraging HIP. So the idea is to somehow deliberately be a little naive in the way we approach this, because we want to take this code from PyTorch and just ask LLMs to kind of make it better by leveraging HIP. And we focus on Microsoft's BitNet, which is a new 1.58-bit quantized LLM. And the reason for this is, it's pretty popular on GitHub because it has about 20,000 stars. And also it does not have, well, it did not have AMD support at the time. So that's what made it appealing. And what Kevin did was, first of all, he added AMD support, and then it also explored how we can leverage the LLMs to increase the productivity of developers and also obviously the performance. And I should say that he told us that this was his first time working with these types of kernels, and with the help of LLMs and obviously his skills, which were very, very good, he was able to get very good results. And I should also mention that, well, actually, I'm sure you already know, but a lot of people are also interested in the RDNA architecture because, most people don't necessarily have access to the big Instinct GPUs, the CDNA, and so they might be just interested in running on their workstation, on their even on their consumer GPUs, and so we're also gonna mention something about RDNA. And so in detail, we have used the Python version 3.12.11, PyTorch 271, which is actually the one you have currently installed on AEC 6, whereas you have PyTorch 2.8 on the other node, the MI 300X. PyTorch was installed with a wheel, and we have the environment has been frozen in the repo. The repo, unfortunately, right now is currently private, so it's within visible only to AMDers, but the plan is to make it public soon. And for what concerns the hardware, we have used the 200 and 300 series Instinct GPUs. We have used the two from the RDNA architecture, so the 6900 XT and then the Navi 3. And then Kevin was also able to access some NVIDIA GPUs, and he has done some work on those as well, A100 and H100. So, I mean, this slide here is probably no news for anyone in this workshop, but PyTorch is currently the most popular deep learning framework. And we also leverage self-attention and flash attention for what we were working with, which are basically two algorithms to improve the way the LLM works. So with self-attention, you allow each token to determine how much to weight other tokens. And there's this little diagram here that's representative of that process that's taken from the source here. And then flash attention basically will improve the memory of your model, memory usage. Okay, so it's also interesting, I think, and I'm personally quite proud of the way this work came about, because our team was at a hackathon in Edinburgh this year, and there was a team from Cambridge in the UK that had a code for some astrophysics simulations that was working with Python and PyTorch specifically. And they were interested in basically translating some of the most demanding kernels that were in Python into HIP, but they were not super familiar with HIP and how to develop in HIP. So I suggested them to try out an LLM to hipify their Python code for them. And honestly, to my surprise, that worked seamlessly. They have used Claude for that, and they fed Claude some Python code. The code that Claude produced was hipified, compiled, ran, and just like that, it resulted in a big speed up. So that was exciting, and we wanted to explore this more and also understand better why this happened, why the speed up. So the first task we gave Kevin was exactly this: like, dig into this and let's understand why that happened. And working with our team and with the help of Andrew Chisholm as well from our team, they found out that the main reason was that basically with HIP, there was a lot of kernel fusion. You were calling so many fewer kernels, and you can see here with PyTorch, they were calling around 30,000 kernels. With HIP, only around 9,000. And that alone was the reason for the big speed up. So we wanted to, keep going into this direction, and that's what originated Kevin's project. So I'm happy about this because this initiative stemmed from something that we did at a hackathon. So I think that's pretty cool. Okay, so this slide here explains what models were considered in this work. So um, we considered ChatGPT, Gemini, and then two open source models. So DeepSeek R1 and then Qwen3 Coder. So Qwen3 Coder is specifically a coding LLM. If you haven't used it, it is pretty good. It's actually a lot of fun, and I recommend you give that a try. Um, and yeah, so among the open source ones, Qwen3 Coder is actually a pretty strong choice, we found. Yeah, so this slide here basically just details Kevin's experience when interacting with these LLMs. And he found that basically kind of switching back and forth from one to another was at times helpful to kind of, in a way, benefit from the skills of each of those models. So yeah, for what concerns where to find the models, you already know about Olama. That's definitely an option, but the proprietary ones you can obviously find online. But then there's also the option for Hugging Face and LM Studio if you haven't looked into those. So for prompting, we talked about prompting in the past couple of days, and I think that because Kevin was using quite large models, he could somehow keep prompting relatively simple. So he wasn't experimenting too much with complex prompting techniques. And that seem to have been enough for him. But obviously there is some back and forth that you have to do if you are not very specific from the beginning. And in fact, he's saying one-shot solutions rarely work. Usually had to iterate around 10 times to make it work. So, we talked about it. It's in general better to be specific because then there's gonna be less iterations, less back and forth that you'll have to do. Yeah, so the reason why we focused on inference rather than training is because we thought that this was gonna be more reproducible by people that were interested in kind of exploring this or just doing the same thing, because with inference you have lower hardware requirements. You don't need to store the optimizers or the backward pass, and therefore you have a much smaller memory footprint. And also, there's always the question of accuracy, and we thought that with inference it was relatively easy to at least define what accuracy meant, because we would just keep asking the same question in the prompt, and if the answer made sense, then we would say that, well, yeah, it's working. Because we did have situations where we would ask the question And the answer was completely bananas, or just like going into an infinite loop. So that's clearly an indication that something's not working. And also, the approach of using inference would allow users to replicate this workflow even on Radeon GPUs, and possibly even on consumer laptops. So we thought that this was going to be uh, a type of approach that would resonate with the larger crowd. Um, yeah, so in terms of the recipe of this work, um, the idea was to start with something, some sort of initial guess, something that was a minimally viable solution, and then basically iterating with the LLM, asking it to optimize it, checking the output, is it correct, is it not, and then basically repeat this process. And even actually by checking the actual performance after a few iterations, because you may feel like, yes, it's correct and it's fast, but let's just actually quantify how fast and how much faster than the previous iterations with some profiling. So profiling will be a topic for tomorrow, so we had to cut it out of this presentation, but just know that Kevin actually did some profiling as well, and that's something that you could even do in workloads and workflows like this one. Okay, so we focused on BitNet, and in particular BitNet B1.58 to B4T. What does this mean? Basically, B1.58 refers to the ternary weights. So this model, as I said, is quantized and uses only ternary weights, so -1, 0, and 1. This is the version with 2 billion parameters that's been trained on 4 trillion tokens. So BitNet is, in short, a llama-style transformer that replaces a llama linear layer. And it's very efficient due to the 1.58 bit weights. However, at the time Kevin started working on this, it was optimized only for CUDA, basically. It was heavily optimized, actually, because it was leveraging CUDA and also PTX code into the kernels. And it made it even more appealing for our work, as I said, because at the time it didn't have AMD support. So the first thing that was done was actually to add AMD support. And we found that, unfortunately, the ROCm backhand did not support some flash attention kernels that we were hoping to use that were pretty fast on NVIDIA. So instead, we had to use the composable kernel operators that were a little slower. And what we focused on was this W2A8 Gen V kernel. So that stands for 2-bit weights and 8-bit activations. And this is the kernel that had the main impact in what we were trying to measure. And it works in this 3-step approach, where basically there's this decoding into in a format. Then there are multiple S.4 that happen, and it ends with a shuffle down accumulate. So what was explored was to introduce PyTorch bindings to a heap kernel, and that's outlined in the next couple of slides. So the idea is to begin by compiling the kernel as a shared library and then call it with C types. And also there's the option of doing a custom C++ PyTorch operator that is fast, allows for greater fusion, but takes a little time to set up. So for option 1, here it's detailing how that has been done. So you should create a dispatch function in heap, then you define your kernel and compile it as a shared library. Notice that we're using heapcc, and then we're providing the dash dash shared option, and then the output, which is what you'll call that shared library. So it's called libbitnet.so. And then you link it using C types here. For the other option, you'll create the directory to hold the operator. Then you create a file in heap with the bindings. And then basically you have to follow along with the other steps that are reported here. So we're not going to go into great detail about this, but these are somehow this is the high level overview of what's been done to achieve that. And so with that, BitNet was able to run locally. So we just ran it on our laptops. I ran this on my laptop. Yes, my laptop doesn't have a GPU, so it was very slow, but Kevin ran it locally on the RDNA that he had access to, and it was working quite well. So the question that we asked was, what is an eigenvalue? And that was the question that we used to check whether or not we've got the right answer. And the warm-up question that Kevin was always asking is, what is AMD? So it's reported here. And here we're basically outlining how it's been, how the workflow that we used is set up to install the software. You see that we used wheels for Torch Vision, Torch Audio X formers as well. And then we installed the dependencies, and then we ran the code with the options that you see here. So we focused on the number of tokens per second as a measure of performance. So here on the top right, you see a little screenshot that shows you what a token is. So a token is not necessarily a word. It can be a chunk of a word, for instance, like you see here, Kevin. It's 2 tokens. But even if it's incorrect, you could think of a token as a word to kind of familiarize with that idea. So what is an eigenvalue was our prompt. And we've got around 128 output tokens as the answer. And we measured the speed of how fast those tokens were produced, and that was our indication of the performance. And so what I show you next will be a comparison where we just ran the initial PyTorch code on both AMD and NVIDIA hardware. Initial, after we added AMD support, then the PyTorch code plus the CUDA optimization for that kernel, and then the PyTorch code with the heap optimization, and that we ran only on the AMD hardware. So basically, this diagram here you see has the different GPUs that this was ran on. So for the 300X, for instance, we're comparing the PyTorch only, which is the orange, and then the heap version, which is the red. And the columns that have those stripes are the ones for which we have set PyTorch tunable opt that I'll tell you in a second about. I think it's in the next slide. But the main takeaway here is to see that basically we've got pretty good performance improvements. And you can see it here, the speed ups over the base PyTorch version were seen throughout all the AMD GPUs that we considered. And in general, we saw larger speed ups for smaller GPUs. And the thing that got us excited is that the MI300X column produced more tokens per second than what Kevin ran on the H100. So obviously this is something that we ran, and it was a highlight of his internship. And it's also interesting to see that with the HIP version, the memory footprint improved quite a lot. So sorry, I put the PyTorch tunable opt slide somewhere. I thought it was going to be after this one, but in short, that is basically you exporting an environment variable that lets PyTorch tune the gem operations so that you select the best one for your case, and you see that in pretty much all cases, turning that variable on improved the performance of the run. Okay, so yeah, as we said, this kernel was the main driver, and Kevin explored 10 different versions of that, but the most relevant are the one where CUDA was converted to HIP, then one where we used AMD intrinsics, and then one where he produced the kernel that was unified for RDNA and CDNA, so that actually worked on both architectures. As I mentioned, this repo is currently internal, so it can't be accessed by anyone that's not from AMD, and all the versions are there, and the aim is to make this public soon so that people can see his work. Yeah, so just a quick mention of what was done to allow RDNA support. So basically what changes between cDNA and RDNA is that they have two different ISAs. So what was needed to add RDNA support was a two-step procedure. Basically, we had to rewrite the attention mechanism from scratch because the XFormer's composable kernel backhand was not supported on RDNA. And then this operation here that was used for the cDNA runs was not available on RDNA. So basically, Kevin was very good at digging into this. So after realizing that this intrinsic was not portable to RDNA, basically he looked at the assembly dump and found out that there is this instruction here for RDNA and this alias that he could work with and somehow make work on both architectures. And so and so using that actually made the kernel portable to both cDNA and RDNA. Oh, there it is. Yeah. So so the PyTorch tunable opt, as I said, is this environment variable that you export. And there's actually this very interesting blog in Rockham blogs that explores that option and how that affects your performance. And as all blogs, this has been added to the knowledge base in your AMD AI assistant. So I think if you just ask the assistant to tell you about PyTorch tunable op, it should be able to give you the details and point you to the blog. So this slide here is just a slide that compares all the different versions that we had for the problem. So V0 is basically the initial PyTorch version, and then you see that from going from V0 to V1 and V2, there's been a lot of improvement, and then V10 is the unified cDNA RDNA kernel. So yeah, so V1 is the one that was porting to HIP using the LLM. And I think it's interesting because Kevin also used as a first try Hippify Perl and Hippify Clang, which are the usual tools that you would use to hippify your code. But because that CUDA kernel had PTX instructions, those tools actually didn't work quite as one would hope for. However, with the LLM, he got very good hippification, and he even told us that the LLM was able to find some intrinsics that were actually poorly documented in our documentation. So you should keep in mind that one more thing you can do with LLMs is actually hippify your code, and not necessarily from CUDA to HIP only, but also from Python to HIP. So, which is, pretty much what we're doing here. So, the whole point of this presentation is kind of like to plant that seed in your minds and open one more door for what you can do with these LLMs. So for version 2, basically what happened was that with this intrinsic at the bottom here, he could replace this entire function. So basically these four int 8 dot products were converted into one single int32. So that, as you've seen in the table, was even more improving the results. And we're not going to talk about V10 because that's the unified RDNA cDNA that we actually already covered. So this is somewhat a summary of what this work taught us, actually, which is that overall, across all the versions that were worked on, the aggregate runtime decreased from 30.85% to 22.44%, which is pretty consistent. And then we also, as I mentioned, did some profiling work. So this is a bit of a teaser for what comes tomorrow. But we saw, we have confirmed the improvements actually also using the profiling tools. And something cool that we also observed was that the wall duration of those kernels saw a 3.84x speed up. So we think that this work was a success, and it showed even more how we can leverage LLMs to, relatively easily optimize the workloads, because you've seen 10 versions, right? But, if you stopped at version 1 already, kind of like channeling your inner vibe coder, that's already good. I mean, we wanted to push it even further, explore the intrinsics and so on, kind of dig deeper. But even just stopping at version 1, that's already pretty good. And that was kind of like the question that we were trying to answer with this work. How little effort can we put, and how big of a gain will that result in? So that was the reasoning for version 1. So this is the environment variable I was talking about, PyTorch tunable op enabled, and you'll set it to 1. And then this is kind of like a more detailed summary and analysis of what we've done, and a deeper reflection on the work that was done in this project. So the main takeaway for this is that LLMs can actually help Python workloads as well to be converted to HIP and squeeze more performance. Obviously, you shouldn't convert all kernels that you have in Python to HIP, but only the ones that you found are the critical ones, that are the ones that in a way decide the performance of your overall problem. So this is it for this presentation. Hopefully you found it interesting, and I got you excited about our internships and hackathons and whatnot. I'm just gonna give it back to the other presenters for more interesting topics coming your way today. Thank you. And as usual, if you have questions, drop them on Discord. I know you cannot unmute, so just be loud on Discord if you want. Go ahead, Bob.
Yeah, I do want to caution there's some comparisons between AMD GPUs and NVIDIA GPUs. That's not an official performance comparison. It's just a work in progress and relative benchmarks to see how we're doing. I think you continue optimizing both of these, on both architectures and improve performance. So we have a comment in the QA section of Discord that very impressive what could be achieved using an LLM to port the code to HIP. And I do think it's eye-opening what you can get out of an LLM, as long as you're careful and don't expect it to give you the correct answer with your first question, but it can help if you work with it and steer it, guide it towards the right solution. We also have a question being confused about the difference between HIP and ROCm, and we're a little sloppy on the terminology as well, but let Giacomo explain that.
Yeah, so I think you should see ROCm as the whole stack in a way. The what's the word? Not the framework. It's like the umbrella that kind of like covers several things, like compilers, libraries, profiling tools. HIP is the language that you use to basically program the GPUs. And yes, the libraries are called HIP-BLAS, for instance, or ROC-BLAS. So as Bob said, there's not a super clear distinction, and at times there's only a library that has the ROC version and not the HIP version. But in general, ROCm is like the software stack that enables running on the GPU and profiling, I would say. And for HIP, you have to think of HIP as basically the counterpart to CUDA. That's the simplest explanation I can give you, I think. It's more nuanced, and I think, Bob, if you want to add anything more to what I said.
Right. I think the biggest, if you keep in mind that if you have a portable makefile, you can set one flag and compile with NVCC instead of HIPCC, and it will switch between cuBLAS and ROC-BLAS. At the HIP layer, if you call the ROC-BLAS layer, you can only run on the AMD GPU.
Yeah, and there's a question about what we meant by kernel. So by kernel, we meant that Gen V kernel that, let me see, I don't remember exactly what was called, W2A8 kernel. It's the Gen V kernel that was ported to HIP.
Yeah.
There's a question about environment variables. So I think, Bob, is it tomorrow that we talk
We
about
only
the
talk
environment
about
variables?
it briefly, even tomorrow, but basically what happens with the PyTorch tunable enabled is it tells PyTorch to run 24 different variants of solving the matrix multiply. There's a lot of different approaches and sizes that it can use. And so it runs those all and finds the fastest one. And then it stores that if you call that same size, it will continue to use the best version for the run, and that can get a speed up of anywhere from 10% to a 2x performance increase. And on different GPUs, that table, and it has to be a large table to cover every possible matrix size and method. It gets tuned for that GPU in our distribution, but not all of them have been tuned extensively. So on our GPUs, if you supply that flag, it will find the best matrix multiply to use. Now you may not want to turn that on if you're calling matrix multiplies with a different size every time. So that's why you have to set that variable. Yeah. And it does make a difference. I think one of the takeaways from seeing these presentations is that yes, it's a drop-in replacement on AMD GPUs for these types of workloads. You just bring your code over and it runs, but you may have to spend a bit of time getting it to the performance improved, which is true of any code. You move to a new platform, you have to spend a little bit of time optimizing it. And our biggest caution is don't just bring it over, get a number out, and say, oh, it's not as good as what we were getting on NVIDIA or on our previous system.
Yeah, and if anyone has doubts on what a kernel is, it's basically just the function that you run on GPU, basically. Very, very simplified.
You can think of it in many cases in a traditional programming source code as a loop. That's not quite true in all cases, but it's basically you're doing a for or a do loop or a nested set of them.
And I think on AEC 6, we have two modules for PyTorch, one that has the tunable opt set to true in the environment and one without, right?
Yeah.
Check.
Yeah, there may be a bug in that optimized module.
Oh, that's actually only on the other one, only on GPU 60.
Yeah.
Yeah, and there's a couple of other flags for MI open that are set in the module. And Bob is gonna show others tomorrow.
Yeah. And I think in particular, I hope you're seeing that if you just go on to your even workstation GPU or data center GPU and do a pip install package name, there's a lot of optimizations that you're not getting, such as GPU aware MPI, the vector instruction set for that particular CPU, and then even in the model that you're running, you can do optimization. So there's a huge opportunity for optimizations here. And tomorrow will be optimizations and profiling. So we'll start to get into those kinds of discussions.
Yeah, I hope we were successful at kind of progressively building this event. We had the warm up on day one, then the first trials on day two, and now it's starting to get hotter and hotter.
Yeah, and more fun.
Oh yeah,
it is getting deeper and more advanced. So we are a little bit over time here, and I want to give some time to Marius to talk about neural operators. So let's go ahead and get him to share his screen and Marius has volunteered to give this presentation, and Marius, you want to introduce yourself? You're one of our European staff, one of our newer European staff.
Yes, exactly. I'm located in Germany and I'm with AMD for now half a year, so rather recent. And I also work in parts on enabling AI application for science. And that's also the topic for my talk today. I hope you can see my my slides. Okay, great. The main thing I want to talk about is one type of applications which you typically run into if you work in a scientific context, especially computational science or simulation context, and that's prediction of time series. So we have some system which changes over time and you want something to describe how that happened. And especially one type of machine learning approaches which got really popular for that are neural operators. And I will also give you a really quick introduction into those. And then we can see how we can apply those neural operators to predict time series of a physical system. So yeah, so predicting time series is a really fundamental task in many fields of computational science, ranging from physics and engineering. And what it basically, or the problem description is basically, if I have a physical system which is in some current state, how can I predict how it will evolve in time? So that can be molecular dynamics, that can be particle physics, or that can be, for instance, also to describe the Earth's atmosphere. So given a current snapshot, which you get from satellite data or from measurements, how can we get the state of the Earth's atmosphere, like for instance the weather, at a later point in time, like 2 days from now, 3 days from now? And if you phrase that in a more mathematical framework, we can say that the state of the system, which here is called U, I hope you can see my cursor, U at some point in time, T0, and now we want some operator R, which when I put the current state in that, it gives me the next state to some later point in time back. So basically it performs some kind of time stepping. And what that means is that this R describes all the physics in my system. So basically the dynamics, if you want to call it like that. But it also means it entails all the possible difficulties of your physical system. It can be chaotic, so really sensitive to small changes in initial conditions and small errors. It can be multi-scale, so there can be really small features, but also really large scale phenomena. And you can exhibit, or you can have exponential error growth, which basically means over time, every small error you make during your time stepping will accumulate over time and lead to large deviations later on. And there are different ways in how we can describe now how this R looks like, so how our system evolves in time. The standard approach, where we have like decades of experience, is in our numerical simulations. So typically you look at your physical system, you try to derive a mathematical model of it, typically in form of some set of differential equations. Then you try to discretize it, apply some numerical methods, and in the end, you get some mathematical description of your problem that you then can solve on a computer. The good thing is, when you do something like that you get a lot of guarantees out of that. So you can basically prove how accurate your result will be. You can prove whether your simulation will be stable or whether it will explode at some point. So it will become unstable and get unphysical in a sense. You can get really, really accurate results if you spend sufficient computing resources on that. But that's also the problem. It can be prohibitively expensive, especially if you look at real systems of interest. Like if you want to model how the atmosphere evolves, or the Earth's atmosphere evolves over time, you will not have sufficient computing power to simulate everything. So you have to make a compromise in some sense and give away a bit of accuracy to still compute it on today's hardware. And then the other approach, which is much more recent, are artificial neural networks. So instead of deriving this R operator from physics, what we can do is we can train a neural network to approximate this function or operator. And the main advantage would be that with neural networks, the training is really expensive, but usually evaluating the trained model isn't as expensive anymore. So the goal would be you look at all the different types of simulations you can do for your physics, and you train it only once. But once you have invested all this compute and you have trained your model, you can evaluate really cheaply a lot of times. So if you want to run 1 million simulations with different initial conditions, different model parameters, for instance, then that's very much cheaper than if you run 1 million numerical simulations. But the problem you get is, of course, neural networks are oftentimes a kind of black box approach. So you don't get this accuracy and stability guarantees out of the box. And you also don't get a guarantee that your model actually performs well on those different types of problems. But it could also be you train it, and then only on those few problems, which are part of the training data, it performs good. And on the other ones, it completely fails. So you don't get a guarantee there either. And lastly, you need the training data to actually train your neural network, as always. So there are quite a few downsides, but also the potential is quite high because numerical simulations are oftentimes so expensive. And so a lot of people are looking into that and what types of neural networks you can use to describe your system and how it evolves in time. And one class that's rather recent are neural operators. So they are maybe 2-3 years old, 4 maybe. And here the goal is, instead of standard neural networks, which typically map between discrete input data and discrete output data, you instead map from functions to functions. So discrete data means, for instance, if you look at an image, it has discrete pixels. Or if you look at LLMs, you have a discrete sequence of individual tokens in your sentence. But for simulations, that's typically not really desirable, since how you discretize your equations and describe your system, so whether it should have 1,000 degrees of freedom or 1 billion, significantly impacts the type of discretization you apply. So you want your model to become independent of the resolution you apply and the type of discretization. So you want direct mapping between functions. I hope that makes somewhat sense. I know it's really dense now, this introduction. If you're not really familiar with the concepts here about neural operators and function spaces, don't worry. Just think of it as a fancy new model architecture. And for the rest of the presentation and also later the exercise, you can just replace it by a ResNet or LLM, and it won't change that much. So don't worry. And the key idea is, if you take the state of your system, which again is this U function, which you can evaluate, like you can measure, for instance, a specific point called xi, and then you pass that to your neural operator, what you will get out in the end is again a function evaluated at a specific point. And you achieve that by only using 2 types of transformations in your model. The first type of transformations are pointwise operations. It's just like a linear layer. You just have a weight matrix and you multiply that on a per point basis. And by doing so, it doesn't matter what specific points you sample, because the same weight matrix will always apply to each individual point. So you don't have a dependency between the points you sample. And the other major operations shown here in blue are global continuous transformations. And there you have a lot of choices what you want to do. Typical choices, you use a Fourier transform, here shown as FFT. You can do continuous convolutions, so not like discrete ones as you use in convolutional neural networks, but instead continuous ones, using kernel functions, for instance. So you have a lot of options. And by doing this trick and using only pointwise operations and continuous global operations, you get this property that you learn from an input function to an output function, and you can become independent of how exactly you discretize your system and what points you choose to measure. I hope that makes somewhat sense. If not, just think of it as a fancy neural network architecture and replace it in your head with a ResNet, for instance. Another problem you have when looking into scientific data sets and benchmarks, or let's phrase it differently, much or a significant portion of the progress we saw over the last decade in AI can be attributed to have established data sets and benchmarks for different tasks in the respective communities that everybody accepts and everybody develops new models for and benchmarks their models against the other ones. For instance, in computer vision, you had MNIST and CFAR and ImageNet, which were really a baseline benchmark. Everybody tested their new models on that. And you have the same in language processing, or also in protein folding with AlphaFold. It was a similar history. But the problem is, in many scientific fields, it's not so easy to do something like that. One of the reasons is that many, especially simulation sciences, have multi-dimensional data. So you have 2D data, so like images, but also 3D data. So you get like volumetric data. And that means individual data samples can become really, really large. Also, you oftentimes have transient processes. So you have a time dependency, which again increases the size of your data set because you add one additional dimension to it. And so you get data samples which can have millions of data points. Just think of an image which can have millions up to, in cases, billions of pixels. So it can really, really become huge and can take several terabytes. So it's not really trivial how to handle those. You have to have the internet bandwidth. You have to store it somehow. You have to pre-process the data. So it's not really trivial. And also, depending on what simulation approaches you use, your data might have a different structure to it. What I mean by that is, for LLMs, you typically have a sequence of tokens. So it's really clearly defined. And for images, you always have a grid of pixels. So you also know what type of data you receive during training. But for simulations, it can be also a structured grid-like structure in your data. It can be a point cloud. It can move over time. So it really is not so straightforward to define a general benchmark everybody can use for the application. I want to show you two examples where people try to do to provide a conclusive data set for simulation. Both were published in NeurIPS, which is the WELL 2024 and PDE Bench in 2022. And both provide a selection of 2D, 3D cases and data sets from different fields of computational science. And they also provide different state-of-the-art models which you train to provide a baseline you can benchmark against. For instance, Fourier neural operator, FNO here, a UNet, or also PINs. So they train it on their own data set, provide the results, and you can now test out your own model and compare against their baseline results, basically. In the following, I will mainly focus on the WELL dataset, but you can also have a look at other ones. And of course, I left out also a few, but those two seem to be quite popular in the field. So let's dive in and pick an example. The one I use for this presentation and also for the exercise you can do later is this turbulent radiative layer 2D case, simply because it's the smallest. So the data set is only about 7 gigabytes large, which is quite manageable. The larger ones can reach up to a terabyte, which shouldn't be installed on a shared system like AAC. So, and that's basically a fluid problem. So you can see on the top right the initial condition where you have two different fluid phases. You have a hot fluid phase, so with a high temperature shown here in yellow, and you have a cold fluid shown here in blue, and basically an interface between them. So you have a temperature jump between the left and the right fluid. And in addition, indicated by those errors, you have relative movement. So you can just imagine that the hot fluid, like the hot air, if you want, moves also downwards, and the cold air moves upwards, or the other way around, whatever you like. The crucial part is there's relative movement, and because of this shear and the viscosity of the system, over time you get these bubbles forming, and which become unstable over time. And later on, you will find that the system involves a really intricate interface between the two fluids at the beginning, and a lot of intricate flow features like small ligaments and so on. So that's not really trivial to predict, especially behind a neural network. And that will be the case we are now trying out. So you can also have a look at the GitHub or the paper if you're interested in the details of what this case describes, but for now that should be sufficient. So when we want to try and train that model, it looks something like this. So we take several time steps as input data just to inform the model or give it some temporal information of how the system evolves over time. How many we take is kind of a hyperparameter and controlled by this n time variable. In this case, it's just 4. And fields is the number of variables or channels if you come from computer vision. So it can be, for instance, because at each point in space, you have a temperature, a density, a pressure, a velocity, and so on, so different quantities defined. So that's this n fields, and nx and ny describe the number of points in x and y direction. So that's basically the dimensions you see here. So you pass those 4 time steps into the model, you get a single prediction for the next time step out, you compute a loss, you do backprop, and you update the model, and you do that over and over again, as you would usually do in machine learning. Now, for inference, once the model is trained, it looks a bit different. If you recall from the beginning, what we want is we want to time step our system in time over and over again until we reach some final time level. And so once the model is trained, what we actually want to do is we want, again, to pass those, let's say, 4 states into the model to predict the next flow state. But then we want to feed that prediction back in the input to predict another state 1 time level further. And we do that over and over and over again until we reach our terminal time level. That's the overall goal. Similar as you would in a simulation, where you would run time step after time step after time step. Or similar to LLMs, where you would basically get a token out as the output of the LLM and you pass it back into the input, something like that. And that's also called autoregressive because you pass the output back into the input. So how do you use that later on to actually run on GPU? Fortunately, that's not too complicated. You do a pip install, and that later you just import. We use the neural operator package here, which is just a reference implementation of the neural operators from the original paper, built on PyTorch. The only thing you have to keep in mind is that PyTorch has to be installed with ROCm support, but if you run on the AEC system, there's a module for that. You used that probably the last 2 days already, so nothing new here. Just for you to keep in mind, you can install all the PyTorch models and packages, and they will work under the condition that, of course, you have the correct PyTorch base installation. So for those who might not be too familiar with PyTorch yet, just so that everybody's on the same page, you need a few key components, of course. First of all, the model. We just import from this neural operator package, so that already implements all the specifics and details. We don't have to do that from scratch. You specify the number of layers you want and the model architecture. And then in the end, you have to add this toDevice keyword to actually move the model and the model weights to the GPU, because later on, we want to evaluate the model on the GPU. You instantiate your optimizer, standard Atom, standard MSE loss, nothing too fancy. And last, data loader, which just you want to shuffle your data set and to batch it into individual mini batches of some size. So again, nothing too complicated here. Also, the training loop, it's always the same few steps. In each epoch, for each mini batch you see, you first nullify your gradients. So basically you reset your gradient information in a sense. Then you have to move the current mini batch you have to the GPU. Again, you can see this to device keyword, which indicates that PyTorch will move that to the device. You might do some pre-processing, and then you do the actual compute. So first evaluate the model, you do the forward pass, and then you evaluate the loss function, compute the gradients, and apply the optimizer step, so the backward pass and optimization. And that's about it. Again, nothing too fancy. But what might be new is, how does that look like on the system? So how does this PyTorch code translate to system activity? So I will show you a profile. No, I missed one slide. So with that implemented, we first can run the training. So we just call this fno.py script, which you can find in the training examples for some episodes, a certain batch size, and that's about it. You can see here, you get a nice progress bar. And one of the key metrics you want to use later to describe the performance of your training is the number of batches you can process per second, which you also sometimes call throughput. It can also be like number of images per second, number of tokens per second, but it's always a similar idea. So how many training samples can you train your GPU on per given time? And you can see here something you will encounter a few times, especially tomorrow, something called a first touch penalty. It's always good to keep in mind that the first time you do something in PyTorch, in Python, or on the GPU in general, oftentimes the first time you do something, you have some additional overhead, because the first time they have to be performed a few additional operations. So if you look at performance, always look at the second, third, or fourth time you do something, and not the first time, because there will always be a bit of penalty or some overhead associated with it. So don't trust the performance results on the first go, just as a reminder. So now we look at how this looks like on the machine. Again, you will get a deep dive into profiling AI workloads tomorrow, but only to get you a feel of what the system actually does once you run your PyTorch code. In the top rows, you can see host activity, so the CPU, what the CPU does. And here you can see two basic blocks for each individual mini batch. First, you see the orange ones, which is this memory movement of your mini batch to the device. And after that, it calls this the forward and backward path shown here in light blue, and then starts over with the next mini batch and so on. Just important to keep in mind that when the CPU calls some PyTorch function and moves it to the GPU, that doesn't mean that the GPU performs the same operation at the same time. You can see the GPU activity down here, and you can see there are a lot of stripes, a lot of things going on. So understanding how calling or launching some workload on the host or sending it to the GPU and actually computing it on the GPU is not too easy. And you will learn how to do that and get more familiar with that tomorrow. But just for now, that you get a feeling of what the system actually does. So one thing to keep in mind in general is that oftentimes when your training is really slow, it's not actually because you miscompute. So it's not because your GPU or the compute capabilities of your GPU are not sufficient, but instead it's oftentimes because your data movement is too slow. That can especially happen if your model you're training is rather small and you have rather large training samples. So you have to move a lot of data to the GPU during training, but the model itself is quite cheap. And that can oftentimes happen, especially for such simulation workloads, because the training samples are so large, and oftentimes the model are rather maybe a million parameters and not like huge LLMs also. So just something to keep in mind. There are a few things you can do. Just a quick a glimpse at what you also learn tomorrow. You can optimize the data movement, for instance, using pinned memory. That also allows you to do some additional, more elaborate optimizations, like doing asynchronous data movements from CPU to GPU, and so on. And what you can also do is you can tune your PyTorch data loader to use multiple threads to prepare the training batches for the GPU. Because every time you need a new mini batch, the data loader has to look at the whole data set, shuffle, select individual items, batch them together, maybe do some additional pre-processing, maybe even read something from disk and ship that to the GPU. So if that takes too long, then your GPU just idles because it doesn't get the data fast enough. So just you can use a few more threads on that and accelerate that just to feed the GPU so that it doesn't stall while you prepare data on the host. And if we use those two improvements, for instance, you can see the same behavior against something like a first touch penalty, but you see that the throughput you achieve is by 15% faster, so you get 15% more throughput than in the standard case. So just as a quick reminder, it's not always the compute, it's more than often it's about memory movement and memory bandwidth when you optimize code. So now let's have a look at what the model actually learns. So overall, the goal is that our model can predict how a system will evolve. So it should learn some physics. And here you can see on the left, the reference, so the ground truth from the data set. And on the right, you can see the predictions made by the trained model. And here you can see a really prevalent phenomenon, which is during the first 1, 2, 3 time steps, the predictions are quite good. So it really matches the reference quite good. But then over time, you start to diverge. And that's really, really typical because of that auto-regressive nature. So because you feed the prediction, which has a small error in it, back into the model, those errors can accumulate over time and you get exponential error growth. There are also other combinations of models and data sets you can find in the original paper, which perform way better. But as I said, that's mainly only for demonstration purposes here. So that's also why the case doesn't perform too well. But neural operators can perform really well depending on the task. So I invite you to have a look at the paper. So key takeaways here. Simulation data sets are oftentimes really hard to handle because they become really, really large, multidimensional, time-dependent, and so on, to just provide them, so have the disk space to send a terabyte via internet and so on, makes it sometimes tough to handle. But neural operators promise to be a really interesting architecture for scientific applications and for time series prediction. But such models in general, machine learning models in general, oftentimes lack long-term stability because those errors accumulate over time. And you oftentimes want to include this predicting of a whole time series into the training instead of having only to predict the next time step. So there's one-shot prediction, but to predict whole trajectories. And lastly, keep in mind, sometimes the data movement is the real bottleneck of a training. So if you're not sure why your training is slow, then attend tomorrow, where you will learn a lot more about profiling and get all those fancy profiling traces I showed before. And now I think my time is over also. So it's time for you to try it out yourself. I think you should be familiar with the setup and how it goes by now. So if you have access to the training system, you can get access to a node via Slurm using the commands you used the last few days, load Rockham, load PyTorch, and then set up your environment. The training example is located in the training examples repository using this path. So machine learning examples, neural operators. You will find the requirements txt file containing all the pip packages you have to install. So just do a pip install and it should work. And then run a few episodes of training, see what happens, see what performance you get. And then there are a few things you can do depending on how much time you have left and how much you're interested. You can test the model on another data set. So you can just play with the command line arguments, just execute a script with dash dash help to get all the options, and you can just use a different data set. Just don't download like terabytes of data. That will be not good, especially for the other ones on the system. So double check before you download anything or use another data set. Replace the null operator by your favorite machine learning model, like ResNet, some Hugging Face model, or whatever you like. Or you can also try to follow the README, which describes the steps you have to do to get this profile trace I showed. Even though that will be the topic of tomorrow, maybe you already want to have a bit of a head start here. So you can also follow the README of this example to do some profiling, or just do whatever you find interesting. I mean, we're here in the advanced part of the course, so I guess you probably have a few things you want to investigate with that. So yeah, post your questions in the chat. I think there will be also a bit of a break. We're a bit over time at 45. And I think next presentation will start at around 3 p.m., if I'm correct. Right, Giacomo, Bob?
Yeah, so thank you, Marius. Really nice presentation. I think the exercises handout should have that GitHub README in it, so you can just jump to that page and try those exercises. Marius, how many GPUs should they grab to do these exercises?
One should be sufficient.
Okay.
So it's designed in a way so that running one episode should take around 1 minute if you have a single GPU.
Yeah. We do have time for exercises and then a break, but conveniently that allows us to maybe look at some of the chat questions that have come up. At 3 o'clock, we will have Alessandro. He's actually got 2 presentations, so don't get scared by this 2-hour presentation. It's hard to sit that long. Anyway, without some break. So we have some questions here. I had a quick question regarding the data loaders and data processing for neural networks. I've heard that there is an optimized version from NVIDIA in the Dolly package. Will this package work with AMD GPUs, or is there another library optimized with ROCm? Hard question.
So to be honest, I'm not familiar with the package, so it's hard for me to tell, but I could check if you're interested.
I think this is a good question to feed into our LLM AMD assistant and see if it comes up with something.
Yeah, definitely.
It's just hard to know everything about every package. The AI space is just exploding. It's kind of scary how many packages are showing up and in heavy use sometimes, but there's just so many different tangents. So let's try that in the LLM and see what that does. Yeah, and there's a little bit of discussions about software deployment. We're very interested in working on this, making especially these AI packages with various ways of configuring them and installing them at sites. So we'd be very interested in working with various centers on what the best approach is, and it's going to be a little different at each site. So how much commonality can we find between the different workflows?
Marie, can you please allow José to be a panelist, because I think he has something he wants to add. Thank you.
And José is coming to us from California today. And has made extra efforts to join us, so we appreciate that.
5:30 a.m. in California right now. Thank you, José.
I think you're live, José, if you can hear us.
Yeah, you're sharing screen, but you're on mute, José.
See my screen, please?
Yeah, we see it.
Okay. So I just want to add a few things to what my colleague said, Marius said. So basically what he has presented is an example of how, we work with AI scientific applications. And he also showed that, in fact, he also showed the impact of tuning certain parameters on the performance of your application as well. via his work. So if you look at the PyTorch data loader, you have different kind of command line or different kind of options that exist. And basically, we can call that a high-level PyTorch data loader optimization, what I'm talking about here. And it is public, and some of these parameters, you can tune that, especially in your AI applications when you are you try to accelerate a little bit of the pre-processing phase. And I have listed here some key parameters that you can play with. When you set up the number of workers, if you look at Marius talk about that, it is in his slide. He was talking about the number of workers, pin memory, preferred factor. What that means in terms of performance for your application technically. So if you set the number of workers, it allows you to define a number of processes that will work in parallel to pre-process the data on CPU. So what that means, it means that it will speed up the compute time, your compute time on CPU. That is the goal of this. If you set the persistent worker to true, this parameter it should not be end here, it should be true here. So if you set that to true, it allows, in fact, it allows to maintain the worker dataset instant alive throughout the training. So instead of after every epoch, instead of recreating a novel process, you will maintain all this alive during the whole experimentation. So it reduces, it avoids paying the cost of reinitializing the processes. Another thing is the preferred factor. As Marius said, it allows you to define the maximum number of batch loaded in advance by each worker. So if you set this to 2, for example, this means that there will be a total of 2 times number of worker batches prefetches or processed in advance across all workers. And the consequence of this is that it prevents GPU inactivities if CPU sometimes struggle. It happens, but the data has to be available for the GPU to be consumed, to consume that. So you can pre-process, you can prefetch some of this data to get it ready, but to make sure that you have sufficient RAM to do something like that. Pin memory, it has, batches will directly be stored in pin memory. That is what it means. So it helps a lot during the data transfer, accelerate the CPU to GPU data transfer. And these parameters are important when you want to accelerate, you want to reduce, what can I say? You are seeing that your AI application is taking too much time and you want to tune it at higher level. The last parameter is drop last. Drop last, for example, let's say that you have a certain batch size. You specify a batch size. And if, for example, the data set size is not divisible by the batch size, it means that you will still have few data left to process at the end. But the best option is to balance workload per process. So, of course, if you set this, it will avoid paying the cost of pre-processing an incomplete batch. But at the same time, you might be losing some data depending on the context. So yes, you can use some of these parameters, some of these options available in the PyTorch data loader to accelerate your application, to especially accelerate the data preprocessing phase of your applications. But you might also be careful and make sure that it makes sense for your AI application you are working on. So that's it. That is what I want to add to what Marius just presented. Thank you.
Yeah, thanks for adding those details. I kept this part a bit short, but that was, I think, super helpful to understand better what does parameters mean.
You also want to add most AI workloads are using the MI300X or our discrete GPUs, but I don't think many people have explored the MI300A with the unified shared memory. And when you start hearing people running these workloads saying the data loading is really what is limiting my performance, I wonder if the MI300A would be able to stage the data and do the transfer from the CPU to the GPU much faster. But I don't think it's been explored much at all. So there's a lot of interesting angles that you can go. Pin memory transfer is usually about 2x faster than pageable memory, and you can think of it, well, I eliminate one copy because you have to copy it to a pin memory buffer to send it. So if it's already in pin memory, you eliminate one of the copies.
And I think it's also a prerequisite in PyTorch to use asynchronous data movement. So if you want to do more elaborate optimization of computation and data movements, then you would also need to set this to true.
And I think there's a question in the chat for Marius or anyone else that wants to address that. Where is it? Sorry. I know that there are new neural networks for long-term stability using Hamiltonian and symplectic dynamics, for example. Oh, that's actually not a question. Sorry, that's just a comment. Do you want to add anything to your comment, Hugo? I know you can't speak up, but if you have a question, feel free to type it on Discord.
And to follow on what Hugo is saying is true about many of the science models that they're trying to build in, instead of just using the generic AI learning techniques, they're trying to build in the physics rules into the models so that they give a physically consistent answer. But that takes a lot more work. So that's emerging across many different models.
Another approach would also be to basically integrate the long-term effects into the training itself. That's also what I meant by not training on a single snapshot prediction, but really training on whole trajectories or rollouts. And there are also different approaches what you can do. For instance, some people use a differentiable simulation code and basically run their simulation with some machine learning model in there, and then they roll back their simulation. So they train it within an actual simulation. Or you could also use reinforcement learning, which might be a more advanced topic, but where you basically evaluate a model and then always steer it or incentivize that it remains stable and gives good results. So there are different approaches how we can also have this dynamical component of a simulation in the model training. But yeah, it's also not really trivial, and there are a whole lot of different approaches and routes you can take in that. So maybe just as a note for those who are more in or deeper in the field and who might be interested.
So I think we'll take a break here until 1500, and you can also do the exercises as well.
Okay, time for coffee. First round.
Oh, geez, that's scary that it's your first round.
Yeah, I need to pace. See you in a bit.
See you. Thank you.
Okay, we'll get set up for the next presentations here. We have some nice comments in the chat on QA channel, a question and answer channel about the MI open variable. And this is one of the interesting things in PyTorch with MI open. It tries to write to a table within the installed software distribution. So you have to set that MI open environment variable to a location it can write to. We do that in our PyTorch module, but if you're importing the software like the example shows, you have to do that yourself. So Seema, you want to kick off the next part with any?
No, you go. It's okay. Thank you.
Okay, I thought maybe you had some
No, I just said I'm
announcements.
coming back. I'm back.
All right, we're glad you're back. And
Yeah, we're waiting for Alessandro to set up access. He had to work around the registration. I think he'd be here any minute.
And we did have a request for Jose's slides on the data loader. We'll try to get those posted. I know he's in meetings in California, so it may be a few hours before we get those posted.
Everyone, how's it going?
Oh, welcome, Alessandro. Good to have you here.
Yeah, I had some issues with this WebEx configuration, but I'm here.
That's just building up the excitement for your presentations, Alessandro. No worries. All big artists do that.
Absolutely. How many people do we have?
I've got about 60.
All right, we're gonna lose all of them. This is gonna be brutal.
Oh, they're loving it.
We appreciate the honesty.
Have you given everybody the good news about what this talk is gonna be about?
No, it's gonna be all you.
We did tell them it's not a 2-hour talk, it's 2 shorter talks.
Okay, good.
Yeah, please introduce yourself as well, if you don't mind.
Yes, I'll try to. I don't know if I'm courage enough to have courage enough to start the video, but I'll try. I feel bold this morning. Here we go. Just a second. I'm gonna blur the background.
We saw a flash. You're just flashing us.
That's fine. That's fine. Never mind. So I'm Alessandro. I work on the Frontier Center of Excellence. I've been at AMD for 5 years and a little more than that. And today I'm going to talk about something that it's very rare to see around, and it's how you use, or in my opinion, how you should use AI in scientific context. The first talk will be more an introduction of what I think good candidates are for AI use. We are going to touch a little bit on surrogate models, but I'm going to say a few things that might be obvious, but it's good for everybody to reiterate that AI is not perfect. Science, it's more reliable. We have been dealing with these numerical methods for a long time. So it's good to remind us that that is safe and solid. And the second talk is going to be more on surrogate models and uncertainty quantification and interpretability of the surrogate model. So it's going to be a little more specific on surrogates. All right. So I'm going to try share my screen if I can. All right.
And we really want that camera on.
Yeah, I'm not sure it's going to happen today. All right. What do you see? You see the whole thing?
We see it, yeah.
Good. It's progress. All right. I'm going to just do one more thing. All right. And I don't see the chat, obviously. So if you have questions, just speak up. I am more than welcome to stop and ask if there are questions and chat a little bit about it. The talk is about 45 minutes, I believe. So we have a little bit time. We'll get a little short break between the two talks, and then we'll do the second talk after that.
Excuse me, Alessandro. People cannot unmute themselves. They will ask every question on Discord, but Giacomo and Bob will tell you if you.
Okay, that's fine. That's fine.
Okay.
Thanks. All right. So, as I said, AI models in theory can replace or approximate computationally intensive physics-based components of your application. But the problem that we usually see is that surrogate models usually struggle, and in general AI usually struggles to generalize beyond the range of data that they were trained on. In particular, when you use surrogate models, you usually have poor prediction for rare or extreme events just because they were underrepresented. And even though an ODE or PD can be, between quotes, solved, it's not really solved, it's kind of approximated, there is really no guarantee that it will always work as expected, as opposed to numerical methods that are based on solid mathematical foundations. There is a little bit of hope with this things that you may have heard of. It's called physics-informed neural networks, or PINs. They are a better option than regular neural network, but they're usually difficult to get to converge. And and to approximate, basically there is an imbalance that may be happening when you train them and when you use them, and things may go a little bit south, and I'll show you an example later on. So given this limitation, what can we really do with AI to improve our traditional HPC applications? And these are my ideas, they're not AMD's ideas. I have some experience about using AI in scientific applications. I've been doing this for more than 10 years now. But here are some examples. You have synthetic data generation. It's pretty safe, depending on what you need to do. Partial synthetic data generation, instead of storing it on disk in double precision with something that doesn't vary much. And I'll show you what I mean in a moment. You can definitely generate at runtime, saving a ton of storage space. So that saves you storage, doesn't save you computation, which is very, very important for certain fields like weather forecasting. It may help you with parameterization, picking good parameters for your model in an intelligent way instead of being based on gut feelings. Estimation, thread definition, decision-making, dimensionality reductions, and so on. So things that are not as exciting as GPT-5+, but it's going to be very, very good for your scientific application. I'll show you practical examples about this. So it's good as an auxiliary component to scientific application, but I don't believe at this point is a full replacement. I'm going to show you codes examples that are in this repository if you want to see them for yourself, but I'll share my screen and I'll show them to you shortly. So let's start with a pretty relatable example, I believe. It's called a projectile motion using a deep neural network. So what did I do? The blue line on the left is basically the solution, the analytical solution of the projectile motion equation, the one that we know from Physics 101. And what I did was giving training on certain initial velocities V0 and certain angles, and including this one that I'm showing to you, this 45-degree and 15 meters per second velocity. And I started just training a neural network that says for position 5, let's say, for this angle and this initial velocity, the projectile would be at y 4.7, whatever this point here is. Sorry, 4.3, and so on. So when you check that actually this works, you see that kind of does it, but it's, even if it got trained on this, it's not perfect. It's not really smooth, but it's okay if you're willing to take a little bit of accuracy hit. The problem comes when I go below the range where I trained on, which is 15 for the angle. I go to 14.5, and the neural network completely blows the whole scenario. Like the boundary conditions are not respected. We go below the ground here, we go up and then down and then up and then down. So it makes no sense. So this kind of to show you that even if you use a deep neural network and you do everything with a ton of data, because this is an analytical solution and you can check a bunch of things, you can produce this data as much as you want, it's not going to get it right when you go out of the range. It cannot generalize well. That's kind of what I'm saying. Better things happen when you use a pin. It uses a more complex loss function, making sure that the laws of physics governing the phenomenon are respected and are part of the loss function. That's the trick. And this helps quite a lot. Again, if we go into the training, the training range, it's very good. It's very smooth. It's much better than before. But again, when we go a little bit out, I mean, this is 10 degrees, it's not 14.5, just to show you that if you go further off the range, this thing doesn't make sense either. Even if it's a pin, it's not going to be a silver bullet. So before I keep going, I want to show you a little bit of differentiating the jargon, what generative models are, what discriminative models are, and so on. So generative models, historically speaking, is not just GPT, whatever, try to learn this so-called joint probability distribution, the P of X and Y, where X is the input data, are the features, what you know, and Y is the output labels, the target of what you would like to know. It basically models everything, the when you know this joint probability, you know everything. With Bayes rules, you can basically come up with the conditional probability, the probability of observing just a feature on its own, and you can do extremely interesting things with when you have a model, a generative model that actually it's well trained. For example, in general, the generative model how the data is generated. You can compute, as I said, the conditional probability distribution, that it's what usually you want, like the probability of seeing something given certain inputs, which is for classification or for discriminating and or for even for regression, like I did for the projectile motion. And also the P of X, as I said, the probability of the input that you can use to generate synthetic data. Some examples of this nectar that you may have, this model that you may have heard of are the variational autoencoder with all these variants, generative adversarial neural networks, normalizing flows, diffusion models, Bayesian generative models, and so on. What is a little bit simpler is a discriminative model, which focuses on learning just this P of Y given X. So instead of learning this whole thing and then do math on it or pick and choose what you want, it's smaller, it's more specialized, and it just learns that given a certain input, you get a certain output. And this is the probability of seeing that certain output given a certain input. It doesn't have a notion of causality. This is not a causal model. This is just trying to model the relation between a certain event being observed and a certain event that will come after that is an effect. As we, there are books talking about this, and it's like you see wind, and you see the trees moving, and there is wind, but you don't know if the tree is moving because of the wind, or is the tree that's generating the wind because it's moving. There is no causality about that. You know that wind means trees are moving. It doesn't know how these are related. Hopefully this will not confuse you more, but that's kind of how these models work. So you should not trust them for causality. You should trust them just for relations. Some examples are the support vector machine, very good old school discriminative model, deep neural network, decision trees, random forest, and so on. In general, generative models are more appropriate when the goal is to understand the underlying data distribution. You want to generate new data, you want to simulate a complex system. Digital twin is one of these examples, as just to mention one. But the thing is that usually generative models are somewhat probabilistic, meaning that you run it twice and you get two different answers, but still consistent with the original distribution of the data. Discriminative models are often the best choice for surrogate models in HPC because they are predictable. Basically, it's kind of, and they are deterministic. Like you can make a prediction in terms of regression or classification, and you don't need to reason in terms of probabilistic predictions. And basically, you get an input, and you always get the same output over and over, and they're simpler to manage. I'm going to show you the first case with an example that I created. It's not the real thing, but as I said before, in wet and climate modeling, which I have some background based on my previous work, the problem is not computing data, it's storing the data that gets produced. The performance of post-processing tasks is often limited by I/O. You need to retrieve these huge amounts of data from tapes sometimes because they are stored in some cold storage place because just there is too much data. And most of the time, you don't really need all this data. In particular, when you do oceanographic studies, when you have sea surface temperature that doesn't variate much on the ocean in terms of gradient, why would you store it in double precision? You can do much better by compressing it with some other smarter method, but that's still what it gets done. So the idea that I'm going to show you here is to train a generative model to replace an entire data set stored on disk. So we are saving space. The approach that I am going to show you is to use a conditional variational autoencoder to generate new samples of temperatures for a particular city. This is actually the highest temperature. So it's not just various temperatures, just one temperature preceded, which is the highest of a certain day. And I'm going to provide the month and the day of the year as a condition to this model. This is a probabilistic approach. So what we want to do is to model the distribution thanks to this model. And it should be, and this distribution that we want to model should be as close as possible to the original one. If you're interested in this, there is a paper that I wrote back in 2018, I believe. Then there are other similar papers that are listed here below. And now I'm going to be brave and I'm going to try to share my browser. Can you see my browser? Probably not.
Okay.
All right, I need to stop the sharing and I need to share my browser. I would like to share my whole screen. So this should share the whole screen. Can you see the screen?
You can
Yes.
make the font a
Okay.
little larger.
Yes, in a second. All right. So this is an example of me. I'm based in Denver, Colorado. So this is all Denver related these are all Denver related examples. And I'm going to simulate, thanks to this very simple equation, the highest temperature in Denver given a certain month and day of the year. You can make it more complicated by decomment this one, this section, if you want to make outliers, more extreme events, but this is what it is. Basically how this works, you pass, this is July 15th, you pass the arguments to this function and you get that the highest is 99 Fahrenheit, which is 35, 34 Celsius, so it makes sense. This is the whole distribution of the data. So this is, for example, for February 10th. I got February 10th as a day. I generated 100 examples here, and this is the distribution of the temperature for February 10th, just made up. This should be something like 32, 36 Fahrenheit, which is pretty cold. More stuff to normalize the data set and so on. And then this is how you create a generative model, the conditional variation autoencoder. You create an encoder class. It's just a neural network. Sorry about that. I'll show you this, and then I'm going to show you another little example more on the conditional variation autoencoder architecture. But this is basically the results of what this modeling is about. So you basically create an encoder and a decoder, which are just neural networks with certain hinted dimensions and some neurons per each dimension, in this case 2 dimensions and 32 neurons each, but I'll show you that I actually use something a little bit bigger. This is just the default if you speak Python. And the latest dimension is basically 2. The condition dimension is 2 because one is the day of the year and one is the month of the year. So what I'm trying to do is I'm going to tell this neural network to generate data conditioned on the fact that I want a certain day of the year and a certain month of the year. And once I train this whole thing with this decoder and encoder architecture, I should get the same distribution by just keeping track of the decoder layer once everything has been trained. So now that I have confused a little bit more, I'm going to go here and I'm going to show you what I mean. And then we will go back to the code. So the conditional variation autoencoder is basically an extension of the variation of autoencoder. You can see it on a book. I don't need to explain it to you, but as I showed you a moment ago, it's composed by an encoder network, a decoder network, and a latent space in the middle. And what happens is you grab all these temperatures with, the temperature itself is part of the input, and the condition kind of goes here into the encoder as a month and a day of the year. And you do this for the whole data set. And then you try to reproduce exactly the same output because you're kind of trying to memorize as much as possible in a latent space that has usually fewer dimensions than the data set. So it's kind of a compression, but it's conditioned to the fact that you want a specific day of the year and month of the year out of it. What happens is that once you have done all this training and this output is kind of similar to the input, I can completely remove the encoder and I can just generate random numbers as a normal distribution with the dimension of the latent space of this basically inner dimension And the data from the original distribution gets generated synthetically. That's almost like magic. So basically, when you want to generate data, remove the encoder, generate random numbers here, put the condition that you want here in the decoder, and the data is exactly distributed as the original data. Let me show you what I mean. Again, encoder, decoder, and here is how we put them together. We create a CVA class, encoder, decoder. The little dimension here, it's I think 50. I'll show you in a moment. The condition is 2, the input is 3 because we have the temperature and the 2 conditions that are part of the input. So you have 3 as input. This is stuff that it's not related to the theory. It's just something that I had to do to get it to work. It's a variation of the conditional variation of the encoder. If you have questions, we will talk about this. I have to cyclically cover the KL divergence. But in the end, that's how you run it. You pick the device, CUDA, which in my case goes onto ROCm because I'm using AMD hardware, as you always should. Input dimension 3, condition 2, little dimension 50 neurons, and this is the network for encoder and decoder. 4 layers, 512 neurons each. Add them as an optimizer, training, the loss goes down until it plateaus, and then we can start making prediction. So as a test, I make a prediction for, I believe, February the 10th. So it's 210, and this is the number that gets out. The real value, it's usually, I just generated a new value, it's 38, but the predicted one is 37.67. So very, very close. As I said, this is a probabilistic approach, so it doesn't need to be exactly the same. It has to be with the same distribution. So the next step is to verify that this variation autoencoder actually learned the original probability distribution of the original data. We need to run some statistics and plot them. So first of all, on the left, you have the real data set for always February the 10th, 210. And you see, this is kind of the distribution of temperatures for Denver. And this is what the CVAE has learned. So by eyeballing it, it's pretty good. It's a little more concentrated around the mean. You see that the densities are really higher here across the mean, but the mean is close. If you print the mean, it's 38.67 for the real and 38.95 for the synthetic, and the variance is basically the same. The shape here is a little off, but it's okay. It's not terrible. If you run other statistics, you see that, for example, the p-value, it's not fantastic, but it's pretty good. It's 78%. The KL divergence is pretty small, which means that these two distributions are very much likely the same. If you have a high KL divergence, this would be much different. And I'll show you right below what I mean. But I want to show you how I generated this again to give you an idea why this matters. The predict, this is how you do it. This is where the magic happens. So as I said before, once you have trained this thing, which happens here, all you need to regenerate the original data set that is huge, imagine on disk, is generating random numbers in a normal way, like distributed as a Gaussian with mean 0 and standard deviation 1. And then you pass that random number to the decoder only, and X as the condition. X, in my case, it's 210. It's February the 10th. And this generates data. You repeat this 10 times, you get 10 different numbers that are all distributed, like the temperatures for February the 10th in Denver that he has seen in the regional data set. It's pretty great. So that is very extreme compression. If you try to do this with discriminative models, you can still do it. You can transform a discriminative model in probabilistic. I told you before that discriminative models are usually not probabilistic, but you can by using certain tricks like the dropout. Dropout is a technique that's used for training to make sure you don't overfit. But if you keep the dropout active during inference, you can actually cut neurons randomly. 20% of the neurons will be cut while you're doing inference, and that will change the numbers in the output. The problem is it gives you the impression that it's probabilistic and it has the same distribution of the original data set, but it doesn't do that because you are not modeling the distribution. You are forcing a discriminative model to be a probabilistic model, in particular, a generative model. I'm not going to show you how I did this. It's all there. We can talk about this or write emails if you want. But you see that when I print out the distribution, this is the real one. This is the one that he learned, which is definitely not the original one. So don't believe that you can get away with a discriminative model and make it generative just using tricks like this. It's not going to work for you. The tail divergence is way higher than before, meaning that these two distributions are not the same. And you can see that the statistics are definitely telling you that these are not the same distributions. Any questions about this? Because I have another example with normalizing flows, but I'm a little running out of time. So are there any questions at this?
It looks like there's no questions on Discord and they cannot unmute. So I see someone's typing, but I guess we're gonna wait and then tell you at the end.
Okay. I have another.
Please go ahead. Yeah.
Yeah, I have another example, and then we can talk for a moment. And if there is time, I'm going to show you the normalizing flow. So the second case is the use of AI for efficient model parameterization. So usually when you have a scientific application, you may have parameters of your model that you need to set. And usually these parameters are configured in a set and forget way. Meaning, you want to model, in this case, snow density, and you know that you need certain parameters for certain geographical area. You set them once and you forget them and you use them in your model and you take the hit of accuracy. That's fine. A better approach is that you can dynamically set these parameters for each case, and this can provide a better accuracy. And you can dynamically set it in various ways, but my favorite way is to use a reinforcement learning technique. In a reinforcement learning setting, usually, but not necessarily, a neural network is used to model what the optimal next action should be. So the policy, it's called, or the values of the possible actions that you have available, and then you select the best based on a quick check on which one you think the action will give you the highest reward. In this case, I'm going to show you a little bit of code that uses reinforcement learning to dynamically select the parameters modeling snow density in an ideal weather model at each time step. So it's not a set and forget, but each time step, you kind of try to set the parameters so that the accuracy is the highest you can. So I'm going to show you this in the Jupyter notebook, but to do this, we use a simple formula involving 3 factors to estimate snow density: the temperature, the wind speed, and the humidity. Each of these 3 factors that are part of your model are weighted by a fixed set of parameters, alpha t for temperature, alpha u for wind speed, and alpha h for the humidity. The problem is to guess these 3 parameters to make sure that the accuracy of the snow density is the highest. You can see here that on the left, for example, you have how snow density gets impacted by temperature with a fixed humidity and wind speed. So the highest is the temperature, the low is the snow density because it melts. In the middle, you have how temperatures impact snow density with different wind speeds. So the highest the wind, the highest is the snow density regardless of the temperature, because the wind kind of packs it together. So you have more density. And then with humidity, you always have more snow density because you have more water into the snow in general. So even if the temperature is high, if you have high humidity, you have high snow density because in general there is more water. In Colorado, we get the blue line. It's very, very dry snow, powdery, and kind of in the lakes area, Minnesota, Chicago, you get very high humidity, and it packs a lot and contains a lot of water. Why is this important? Because estimating snow density is good for estimating water supplies. In Colorado here, middle of the States, in the mountains, if we don't get snow, we don't get water. So estimating how much snow and water content is in the snow is very, very important for understanding how much water we're going to have during the dry season during the summer. So high accuracy is important for this. And this is just the density, the snow density modeling that generates those pretty charts. And then we have the reinforcement learning approach. So I used GIM and I modeled this basically this model as a game. Each time step, we need to guess the right alpha T, alpha U, and alpha H as an action, as you can see here, to make sure that we get the lowest hit on the estimate of the snow density, which I already know during training, of course. So during training, you already know how much snow density you have. You also know the temperature, the wind speed, and the humidity. And you want to make sure you learn these alpha parameters as close as possible, so as intelligently as possible. So for each time step in the real world, you pick them in a way that optimizes basically the accuracy on snow density. This is kind of how I generate the real snow density. The real parameters that we are trying to estimate are 1.5 for alpha T, 10 for alpha U, and 0.5 for alpha H. I do the training. This gets trained, bunch of output, and then we test it. So to test it, this was 10, this was 0.1, I believe, and this was 1.5. And here I imagine a scientist that knows what it's doing, or he or she is doing, and it picks parameters that are very, very close to the real ones, to the one that we're trying to estimate. Remember, 1.5 was the real one. The scientist picks 1.4. This was 10. The scientist picks 10, and this I believe was 0.1, and it picks 0.2. So the scientist, 0.5. Sorry, these are the true. So the scientist fixed this, and then we compare after a few iterations how much accuracy we have lost by fixing the parameter instead of having the reinforcement learning algorithm estimating the parameters for you. We do this test 50 times, so 50 time steps. This is the output. And total, so the reward is negative. Basically, you get 0 reward if you nail it, if you perfectly guess the snow density for a certain time step. So optimal case, when everything is perfect, you should get a total reward of 0. If you get a very, very negative reward, it's worse than a less negative reward. So, and these are the final results. The total fixed reward, so the fixed reward meaning the reward for the fixed parameters by the scientists that were very close to the real ones, is minus 1,383. The reward for the parameters that are picked dynamically for each time step by the reinforcement learning algorithm is just 322. So just with this approach of setting the parameters dynamically for each time step for the real accuracy, you can see that the final accuracy of the density is much, much higher than expected. This is just an example of what you can do, but you can set thresholds, you can do refilling of matrices for your numerical method in a more intelligent way than just random numbers. That's a very safe use of AI for scientific computing, like estimates where you don't have a right answer and the AI is probably going to give you a better answer than your own gut feeling, or basically parameterization that are very much data driven. The last example, which I'll show you in the next talk, is a surrogate model. And it's basically a source term estimation problem. What is a source term estimation? Is about finding the location and the strength of something that has been released or emitted into the environment. Source can be chemical, a gas, a pollutant, radioactive. So you have a source of something. And based just on sensor readings, you cannot see it. You can just sense where geographically the source is. You can estimate where it is and how strong it is. Usually where it is, it's the real problem. Strong is a different problem. But in scientific context, you usually have measurements and a mathematical model on how the substances spread. And the goal is to work backward from the measurements to the source. So this is called an inverse problem, where we start from the effects and we try to find the cause by working backwards. It's a very complicated problem to solve. It's an ill-posed problem. I'll show you what it means. In a traditional way, this inverse problem can be solved by running multiple simulations on where the source might be, and then assess whether the effects are consistent with the observation. So it's a guesswork. You see the source there, you say, probabilistically, the source might be coordinate X and Y. You run a model from where you think the source is, and you see if the effects that come out from the model are actually consistent with your observations. So you need to run many, many iterations of this process with multiple simulations. And imagine this was used, for example, for Fukushima when there was the disaster. You could not see what the damage was, but you could sense it with radiation sensors, and by looking at the plume and measuring the plume, you can actually understand where the source is, where the disaster was, how big it was, what the status was, and all of that. But it takes time. So in those situations, really want to go fast. AI is very effective in solving these kind of problems. And for this example, I will use a heat diffusion problem where I have a plate, I have a heat equation that drives the physics, I have 4 sensors on this plate, and I have a source that is placed randomly, and I need to understand, and the neural network needs to tell me where the source is. I don't have a video ready, but I have a bunch of videos in the next talk. So right now I will conclude, take questions about this, take a break, and show you the next talk with all the source time estimation stuff. So the purpose of this talk was try to convince you that AI can be used to enhance traditional HPC application, but it's not a full replacement yet. Why is it the case? Because you can't verify it easily. You can't trust it. And next talk will be all about building trust on this. So stick around. It is good to make optimal decision, hopefully. Parameterization, generate synthetic data, approximate functions, and so on. What I recommend you to do if you really want to explore this, start exploring this, is to replace small parts of an app with some AI, understand if the input may change, and how that affects the AI, and then make sure that you try different models. There is no simple model approach that works well for a certain problem. You may want to use the conditional variational encoder. You may want to use the normalizing flows. You may want to use the GANs. Depends on how accurate you want your result to be and how much time you have and how much time you're willing to spend on it. Pins are a good and valid option, but it's not that it's a set and forget approach. You always need to make sure that things don't go south. And in the next talk, I'm going to talk about this very important concept called model interpretability, which will make you understand what the model learned. So you know what the model is going to do in certain situation. And my suggestion is to think a little bit out of the box, not as a scientist in the field of CFD, I guess as an example, but more in a computer science terms on where can I use AI to actually improve the performance of my app? I don't have to use AI because everyone is telling me I have to use AI. I have to use AI because I have a big problem like IO. I don't know how to store this stuff. How can AI help me in this? Can even AI help me in this? And yeah, that is a good case. If you have a very good numerical model, a numerical method that is very reliable and quite fast, don't bother using AI on that, even if numerical methods are your thing, because AI is not going to improve much. And I will take questions. Thank you very much.
So there's a couple of questions in the chat. I'm going to feed them to you, if that's okay.
Yeah.
Is it a good idea to use synthetic data embedded in such models to be reused to act as training data for a full surrogate model? For example, a 2D weather forecast model. This is some form of lossy compression.
Mm-hmm.
Will we lose a lot of information?
That's a good point. Yep. It depends on what you're doing. So I went a little bit fast here. Some quantities are very are very good to be generated synthetically because they don't variate much. So it's a lossy compression, yes. But do you really care about losing a little bit of accuracy for sea surface temperature when it's something that changes very slowly and very sporadically, like in terms of the ocean. So that you can take that hit. You don't need the double precision. You can have a sort of a lossy compression for sure, and that is going to save you a lot of data. And yeah, you can feed it to, for a surrogate model just to make sure that they have the data, but it doesn't impact much. Or if you have a quantity that it doesn't impact much what you're trying to do, but it's required, that is a good case that you don't want to store that quantity, but you want to generate it right away and saves you some space. If I'm thinking about more edge devices and stuff that doesn't have a lot of storage. But yeah, stuff like the highest temperature, that is just a number or something that that during the summer is hot, and the sea surface temperature are good candidates. Other thing that I would not apply this approach for, wind speed, wind direction, things that are more, for example, if your case is to predict how much wind energy you're going to produce with windmills. Using surrogate models trained on synthetic data for wind speed and wind direction is a bad idea because you need accuracy for those quantities. Doing it for, I would say, yeah, temperature of the day may be good because it's not going to give you a big impact. Are you going to do this in Kansas where it's all flat and the wind blows left to right and nothing changes it? Well, even if at that point you can even approximate wind direction because it's not going to change. Are you going to do it on the Himalayas where it's all a mountain? You have to be double precision all the time. You cannot assume anything because it's all a mountain. It really depends on use cases and where you can get a hit in terms of accuracy. So yeah, that's a good question, but you need to kind of understand where you can deal with a little bit of loss.
Thanks, Alessandro. And we've got one more from Maxime at HLRS. This is a bit of a long one. How do the limitations and quirks of floating point precision affect modern machine learning models and tools? Many models, especially those involving high-degree polynomials, seem prone to numerical instability due to these precision issues. Gradient-based optimization relies on small, precise updates, so wouldn't limited precision lead to noisy gradients, vanishing updates, or divergence? It seems like this should produce unreliable or even nonsensical results. Yet, in practice, we've seen remarkable success of ML and AI systems in real-world applications. How is this apparent contradiction explained?
Well, it's not a contradiction. It really depends on how the range of numbers are dealt with. There is a very, very, very interesting paper. It came out recently showing that pins do not converge if you use single precision sometimes. So if you want to train a pin that does scientific computing with all the range of whatever, I don't remember exactly what they were doing with the pin in terms of solving the ODE or PDE, but they were using a pin and they could only get it to converge because of this gradient, based optimization, only in double precision. They could not get away even with single precision. That was a great result. It's on our archive. I'll try to find it. So yes, it's not a contradiction. It's really a case-by-case thing. In real world, there are the mixed precision. It's a trick that we use to actually move the range of data from that. Basically, we move the range of data to be representable in FP16 by certain normalizations. It gets done automatically in PyTorch or other frameworks, so you don't even see it. For certain cases, like physics cases, where you may have certain solvers or certain equations that do not fall into that, you get stuck even in single precision. So no, for scientific computing and AI and pins and things like that, reduced precision might not be usable. You need double precision. There is no contradiction there. It's just a case-by-case thing.
Thank you, Alessandro, and thanks, Maxime and Ashwin, for the questions. There's
Yeah,
go
there's
ahead, Bob. Sorry.
a couple requests for those references, Alessandro, but we'll post those
Mm-hmm.
once you get them to us. But I think the questions, and Alessandro making a good point, those of us who are watching trends, as we move into AI for science, which is new, we'll see that there's going to be a need for higher precision.
Yep.
And maybe a broader distribution of precision choices depending on the model you're running.
Yes.
And so it's concerning to us that there is such a push towards reduced precision for AI for science. There's other AI niches where that's fine. But in science, we're going to need to have a rich variety of precisions available, up to double precision and at least synthetic quad precision. So, and we're going to have to get smarter on how to use it.
Yep, I agree.
Very good points from the questions here. I think you're bringing that out.
Want to take a break, Giacomo? It's up to you.
Yeah, let's take a break until 4 p.m. Central European time. So that'll give you a chance to get a drink of water there, Alessandro, and join us back
Or
then.
Gatorade.
The stock is gonna be wild, so get ready, get some coffee or something.
Maybe you can go get a ski run in the break. I think it's been snowing there, hasn't it?
Here in Colorado?
Already?
Oh yeah. We're actually getting, there's a tropical storm, which is the remnants are all over the Rocky Mountains. They're having flooding. We've had rain straight for 4 days, and the mountains are getting snow.
Here it's 28 Celsius in the meantime. Okay, let's
Simon's
see.
going to jump on a plane here and join us for the skiing.
We won't talk about the European weather.
It was good to bring up weather. That's always a good discussion topic, Alessandro. Okay.
Okay, see you later.
Okay, we're approaching 4 p.m. and if Alessandro can get his slides up.
Look at that. I also got the webcam going.
Ooh,
Look at that.
mystery man shows up on video.
You guys see the link in the chat that I posted, or it's something that is just telling me that everyone is seeing it, but it's not true.
We got it. We put it on the guides
Oh, good.
chat channel. Yeah, that looks like a really good reference.
It's fun. It's a fun read. Very short, but it's good, to the point.
Okay. The suspense is killing me, Alessandro. You're going to go deeper on this one?
Absolutely. This is gonna kill everybody. This is gonna be brutal.
Okay, take it away.
All right. We're gonna talk about AI surrogate models, interpretability, and uncertainty quantification. So, as I said before, we're gonna talk about an inverse problem, and the solution is gonna be based on AI. It's gonna be the heat source term estimation problem solved with a neural network. Going to introduce what a Bayesian neural networks are, how we use them for uncertainty quantification, and we're going to see a little bit of interpretability. So kind of number two here is well, you need to buckle up if you're not familiar with this stuff, and where I may lose you, all of you. Usually that's the reaction I get, but hopefully this will be a different crowd. And the interpretability of AI models is going to be quite fun, honestly. All right, so as I said before, inverse problems, basically the inverse problem of heat source term estimation is used as the example. Surrogate AI models, as I said before, can be used in HPC, but you really need to understand what the model has learned, if you can trust it, how it is going to behave in rear extreme events that he hasn't seen during training, how to quantify the uncertainty in the predictions, kind of understand how sure the model was to give you a certain prediction. Is it lying to you? Is it trying to best guess? How to interpret what the model learned? How can you know what the model has learned inside the black box? What features are the most meaningful for the model? Do you really need all the features? You may need less. How big the model should be? How many layers? How many neurons? And how much data is enough? Because data is where usually the money is, where the where the cost of training is. You need to gather the data. So let's talk a little bit about a source time estimation. I'm going to show you how I solved this problem 2019, something like that. And then we're going to build on top of this to see how to improve it with probabilistic method, with uncertainty quantification, and so on. So a source time estimation, as I said, it's basically you have a source of something, a bunch of sensors, and you want to know based on only on the readings of the sensors where the source is. As I said, this is an inverse problem. We start from the effects, so what the sensor get, and we try to find the cause, where the source is. This is called an ill-posed problem, and it's a very precise definition, and it's got three basically part of this. It's non-unique, so you may have the same readings, but the source may be somewhere else in two cases. Instability and non-existence, so you may not have a solution. Inverse problems, as I said, can be solved by running multiple simulation where the source might be, and then assess with various methods whether the effects are consistent with the observations. In this particular case, I have a 2D plate, metal, whatever metal you like, with 4 thermometers close to the corners, not exactly at the corners, but close, and a single heat source that is placed randomly. And we want to find the position of the source based on the readings. And everything is driven by the heat equation. AI is incredibly effective in, between quotes, solving these problems. It's not really a solve, like precise solve, but it's more like an estimate. And this paper uses TensorFlow probability for doing the study. Instead of, for this case, I rewrote everything with PyTorch and Pyro to actually make it compatible with PyTorch. So here's how it looks and how it's, let's say, configured. Source, 4 thermometers, and I store the readings, and there is a simulation running for 200 time steps. And what I do is I keep kind of a buffer of these 4 readings for a window that has 20 time steps. So I keep track of the latest, the temperature before, the temperature 2 steps before, until the temperature 19 steps before, and for each thermometer. I feed it to a neural network, and I get 2 estimates for the X and Y coordinate on when the source might be. The neural network is based on these layers that are kind of old, and they're called the long short-term memory layers. And and there is 1 linear layer for the output to generate these 2 linear numbers. As I said, there is a window of 20 time steps. LSTM layers take a buffer as a window, so that's how I deal with this sort of window. And then you get this sort of a matrix, 4 by 20. You can see it. The plate is 50 by 50. You don't care, it's all normalized. The thermometers are perfect, and they're located at 5.5, 544, 44.5, sorry, 544, and 44.44 in terms of coordinates. How do I do the training? I do a fixed number of simulation with randomly located sources, and I feed it to the training, and then I do some, more random sources for testing, and I see how good it is. This is how it looks. So you get this actual source is the blue dot. The sensors are the thermometers, the axis, the red axis, and the green X is the estimate of this X and Y that is given by the neural network, and see how it goes. It's a little small, I cannot make this bigger, but you see that while time passes, this thing converges towards the source. So case closed, we win. It completely found this thing. Can we trust this model to understand where it's going on fire? Do you know? I don't. So let's try to give a little more context on how uncertain this system is, this machine learning model is, and see if we can trust it or how we can prove our trust in this. So what do we do? The model seems to behave most of the times. Do we trust it? Was the training set representative enough? Do I need more data? Do I need less data? Was the model complex enough? Do I need more layers, more neurons? Was the problem formulation good enough? Are 4 thermometers good enough? So to answer this question, here are what we're going to do. Uncertainty quantification, which allows you to understand how sure the model was about a prediction. We're going to see the systemic uncertainty, that it's about the model itself, and how accurate a particular prediction can be in the best case on the problem itself. And this kind of gets quantified with aleatory uncertainty. There are various models that you can use. I really like Bayesian neural networks. Another one that I really like is Gaussian processes. But also there are older methods that are still valid, which are the polynomial chaos expansion, for example, and others. After that, we want to interpret what the model has learned and how. To do this, we use this this method that it's very obvious, but is now very popular, and it's called knowledge distillation. You can knowledge all GPT-5 into a model that has fewer parameters, and you get almost the same performance. It's been around forever, and now it's got all this popularity, but that's what we're going to do. We're going to distill this model into a model that it's actually interpretable. So we can open the box and see what this distilled model has learned from the main model and make assumptions on what the main model has actually learned. All right, buckle up. Difference between a traditional and a Bayesian neural network. Traditional neural networks have deterministic weights. Each connection in the network has a fixed weight. It's a scalar, it's a number that is learned during training with forward and back propagation. You run it 100 times, you get 100 times the same answer. This has the risk of overfitting. What does it mean? It means that if you train a lot on a lot of training data, basically memorizes this training data and these numbers inside the parameters, these weights, it just memorize in a compressed form, if you want, if you may, the training set. And basically this leads to poor generalization on new data, like I showed you before on the projectile motion case. Bayesian neural networks are a little different. The weights are not numbers. The weights are probability distributions, capturing a range of possible values. So every time you do the inference, you are not reading a number, you are sampling from each distribution of each weight. I'll let this sink for a moment, and I'll show you a chart that will clarify a little bit. So we don't have numbers, we have probability distributions. Every time we make inference, and training of course, but when we make inference, we get a different number for the weight because we're sampling from each and every weight, and the answer will be different, but consistent with what he has seen in the training set. So this allows you two things. It gives you a distribution as output, so you can make considerations in probabilistic terms. So you can actually understand the uncertainty of the weights. So it tells you a little bit how sure the model was about that certain result, and also has the effect of reducing overfitting, because the Bayesian framework does not stick with one number, which is the maximum likelihood number in statistical terms, but it has the whole distribution on each weight, and it considers all the numbers for those possible weights, weighted differently because it's a distribution, but all those numbers that may be right are still considered, on top of the distribution. So let me show you this, and then I'll take questions if there are any, if this is very, very confusing, because this is always very confusing. On the left, traditional neural network, inputs, weights, and outputs. The W's are the weights, and they are all numbers. They are scalars. They are fixed. There is nothing else happening here. You feed the same input, you get the same output all the time. O1 or 2 are the two outputs. They are numbers. They don't change. Bayesian neural network, you may have a mix of scalars and layers where you have distributions. In this case, they're all normal, because a normal distribution is basically gives you the uncertainty on a certain scalar number based on the mean, where the main number is, and the standard deviation, where the number might be kind of a cloud. These, having weights represented as a distribution, gives you the opportunity to quantify the systemic uncertainty. And I'll tell you in a moment what it is in a more defined way, but it's how sure the model was about a certain prediction, how how sure those weights are based on certain inputs on a certain output. The output can also be probabilistic at this point. So they're not numbers, and these are not weights, are the output. And having random numbers, basically distributions on the outputs, allows you to quantify the aleatoric uncertainty, the uncertainty of the phenomenon that you're trying to model. It's something different from this one in the weights, from the systemic. This is something that is specific to the phenomenon that you're trying to model. Tell you in a moment what it is. We will get back to this if it's not clear. Are there any questions about this? We can always come back to this. But, okay, let me show you a few pretty pictures, and then to refresh a little, to cool down a little bit, and then we'll start talking about systemic uncertainty, aleatoric uncertainty, and then we need to get back to the model if there are questions.
Yeah, Alessandro,
Okay.
before you continue, sorry to interrupt, there's a question from Maxime. Do Bayesian neural networks exhibit the same sensitivity to prior selection as traditional Bayesian inference methods, such as Markov chain Monte Carlo?
Absolutely. I'll talk more about this. There is a slide about this. Yes. Yes. So you have the source here in the middle. And this time you see that in the predicted source here, I have a plus minus, and it basically is what came out from running multiple times and sampling from the output, and now are random variables, the estimates for the coordinates. You see that the source is here. This is kind of how it is. Even though the mean is converging toward the source, which is what we saw before, we have an uncertainty of plus or minus 7 points for each coordinate. So you can't really trust this thing. That's kind of what I want to show you. Even if the mean goes there, so everything is good, you think it's fine, the source might have been here, up here. It's around 32, it might be here, plus 7 or 8, or here, you know, it's just so off. And this is kind of a combination, this result is a combination of both systemic and aleatoric uncertainty. Now we're gonna split them and see which one is the most responsible for the bad results. So the idea is to use distribution that model the whole set of possible weights for Bayesian neural network. It's kind of how it works. So this answered the question. And the distribution is assigned by the user or engineer with a prior. So you are the data scientist, the scientist, the engineer, and you say, okay, I want to model this thing as numbers. So I have coordinates, so I have numbers, and I want to use a Gaussian distribution. If you want to count stuff, if it's a flip of a coin, if you count, you want a Poisson. If it's a flip of a coin, you want a Bernoulli. But it's up to you. And then you put a prior on it based on what I'm about to tell you. And that gives you kind of a domain expertise that you have in mathematical form that you can add to the Bayesian neural network that can help model this phenomenon. So the posterior distribution, which is kind of what gives you the final weights of the network, is learned in a Bayesian way. And there are various ways of doing it. There is Markov chain Monte Carlo, which is the most Bayesian method ever. Sample from the posterior distribution of a model parameters, and unfortunately, because of the nature of Markov chain Monte Carlo, it's very slow and it's hard to use in real application. There are no assumptions about the form of the posterior, so it's very safe to use, but it's an overkill usually for what we need to do. Variational inference is what the majority of frameworks that allow you to build Bayesian neural network use. Basically, they compute this posterior distribution as an optimization problem. Instead of directly calculating the posterior in a Markov chain Monte Carlo, so instead of sampling, it approximated by selecting a simpler parameterized distribution, which is called the variational distribution. It's basically a multivariate Gaussian, and adjusts its parameters to be close as possible to the true distribution. So it's a surrogate of a real posterior. It's still pretty good, but the good thing about variational inference is that it's an optimization problem, and you can use all the machinery that is available in PyTorch, TensorFlow, whatever you want, to do gradient descent, to optimize parameters based on a certain distribution. So it goes very fast, as opposed to Markov chain Monte Carlo. It's a little approximation. It's an in-between. The other thing that you should never really do, because it's not Bayesian, but some people do it anyway, and they claim it's Bayesian, is Monte Carlo dropout. You basically, what I showed you before, you do the training with dropout, and you also use dropout in inference. So you generate random outputs, and you claim that that is the uncertainty of the model, because sometimes you remove weights connected to neurons connected to your network, and that gives you the uncertainty in the parameters. It's absolute nonsense. You can do it. It may help you a little bit, but it's not really Bayesian. I will go for the first two. As I said before, random variables can be used for internal weights, outputs, or both. Output as random variables quantify the aleatoric uncertainty. I'll tell you in a moment what it is in a non-formal way. And the internal weights as random variables quantify the systemic uncertainty, the uncertainty of the model. What are these two? So aleatoric uncertainty is caused by the inherent randomness or variability in the system, is the randomness in what you're trying to model, in the phenomenon. This cannot be reduced by gathering more data. You say, oh, this thing is so inaccurate, let me gather another million data and it will get better. It will not, because it is part of the system. It's right. It's like you're trying to try to predict the outcome of the rolling of a die. That is a random phenomenon. You cannot get it right because it's inheritive random. You can have 1 trillion data points on throwing this die over and over and over. It will still be random. There is nothing you can do to improve this sort of uncertainty. Weather prediction, same thing. Even with a perfect model and sensors, minimal variations that may happen at any time cause major changes in the prediction. Is in the process, is in the phenomenon. It's chaotic. It will not get better with more data. For our model, this plate, aleatoric uncertainty represents a fixed level of measurement or model error regardless of the conditions. In particular, it's the amount of thermometers that you have in the position. That's where it is. If you have 4 thermometers, there is only so much you can do with that, because 2 sources close by may provide almost the same readings within the noise. So that is the aleatoric uncertainty. The systemic uncertainty is caused by the lack of knowledge or insufficient data. It's the poor modeling scheme, the poor model that you chose, the data that is not sufficient. And this uncertainty can be improved by using a better model, more complex model, or more fitting model, and gathering more data. So, for example, AI model trained on biased data, systemic, because you have not seen the whole range of data possible. It's biased. And when the model sees something that it hasn't seen before, that variability goes up, and it's within the weights, it's not within the outputs. For our model, this represents how sure the model is about a certain prediction based on the data seen during the training. So multiple runs of the same model. So you run the same model multiple times, and you sample the model parameters, and that will give you a range of possible values, and then it's how sure the model was. Now, I'm sure I confused you even more. Questions? Are there any questions about this? Should we go back to the model, to the architecture? So I show you where the systemic uncertainty, the aleatoric uncertainty live.
No questions in the chat as of right now.
Okay, so let's keep going, and then we'll see if there are questions at the end. Okay, I believe these are just pictures, and I have videos in the next one. Yes, let's go with the video, with the good stuff. All right, let's start with aleatoric uncertainty. Again, aleatoric uncertainty cannot be improved by using more data. It is intrinsic in what we're doing. In our case, we have only 4 sensors. And of course, if you get two sources that, for example, one is here, one is here, they're very close, you may get almost the same readings, and you may get something that falls in between. So it's not good in one case or nor the other. You see that here, the plus and minus numbers are close to 8. So it's quite big. Let me show you. And this kind of measle-like pattern is the samples that are sampled from the output random variables. So I did like 50, I believe, samples. And this is how far they spread. This should give you the crips, because without this information, you may think that this model is great, it's doing everything good, but actually, look at this. The source is here. This thing is sort of moving here, And you may feel good about it because the mean now is reaching the source. But for all we know, oh, sorry about that. But for all we know, the mean is here, but the source might have been here. This was one possible case as far as statistically we are concerned. So this is part of the ill-posed problem. It's like why it's so complicated, because it's not unique. It may not be unique what you're reading. And this tells you that you should never trust this thing. It's close. You got lucky because there are another case where you may get here and it's completely off. Let's see with 9 sensors and see how that changes. You see how much smaller this thing is. It's 3 instead of 8. So with 9 sensors, you reduce the aleatoric uncertainty, not because you got more data, because you changed the problem. And now we are happy because we know that all the samples, all the 50 samples, are within the range of the source. So this is so much more accurate than this one. It seems obvious, but seeing it, quantifying it, it will help you understand if your model is really doing what you want. This is science. You can rely on this, even though it's a machine learning approach. Let's see the systemic uncertainty. And in this time, to see a little bit the difference in the systemic uncertainty, I intentionally reduce the number of training samples to see how much it will change. So it's basically it hasn't seen much. I am just sampling the model parameters. I'm not treating the output as random variables. That's how you separate it. If you sample from the variables and you run the model multiple times, you get both uncertainties, but usually the aleatoric uncertainty dominates in various fields, the systemic uncertainty. To see just the systemic uncertainty, you basically treat the output variables as scalars, not as random variables, and you just run the model multiple times, one after the other. And this will give you a set of samples that kind of show you the systemic uncertainty. So you see that it's 2 now, plus or minus 2. It's still pretty good. It goes where it needs to go. Of course, if it doesn't go where it needs to go, because we are still using 4 samples, 4 thermometers, even though we are not using showing the aleatoric uncertainty. But you see that with 10 samples, we have a 2.1 variation. So it's not great, but it's not terrible. Just with 10, we really do good things. If we use 50, it's way smaller. This tells you 2 things. First, that 50 is enough. You don't need more. So you save money by just going with 50. And the fact that being this small, it gives you an idea of how much better this could go in terms of with a more complex model, what you can do. It doesn't get much better than this. You don't need a more complex model. You don't need more neurons. You don't need more layers. It's just plus minus 1. Your problem with an inaccuracy with this model, it's not in the model. It's in the formulation. It's in the number of thermometers that you have that it's not enough. That's it. This is kind of concludes the Bayesian part, the uncertainty quantification part. Then we're going to knowledge distillation. I'm going to stop for a moment and see if there are questions, because knowledge distillation, it's easy. Any questions, doubts about this? Do you follow this? Should I repeat something?
There's a question on Discord. Is truncation and round-off error due to lack of precision interpreted as aleatoric or systemic uncertainty?
I would say systemic. It's part of the model.
That's the only question we have right now.
It's part of the model. It's just the model doesn't do it right, so you need a better model. The aleatoric uncertainty is part of the phenomenon per se. You need to change how you get the data in. Or thermometers are not enough, or you're trying to guess the flip of a coin. There is nothing you can do about it. Knowledge distillation, as I said, is a technique for transferring the knowledge learned by a large model, which we call the teacher, into a smaller model, which we call the student, without sacrificing too much predictive power. So how does this work? The teacher is something that you trained. It's a big model, has learned an approximation of a very complex function that basically drives your phenomenon, the thing that you're trying to model. And it's trained on the original data. The student is not trained on the original data, but is trained on the teacher's output of certain inputs that you can generate as much as you want. You know the input of your problem. you usually don't know the outputs. So what we are trying to do is we're trying to train the student on the output of the teacher, and it's trying to distill the knowledge of the teacher in a simpler way. If the student model is easy to understand for humans, I'll tell you in a moment what it is, so it's interpretable. Once this training is done, we can interpret what the main model learned, and or we can use the human readable rules that are part of this easier student model. Some example of good student models for interpretabilities are, for example, the decision trees, the random forest, linear models, symbolic regression. These are some of the good ones because you can read with your own eyes what a decision tree does. It's a bunch of if then else statements. You can basically extract them, write them in C or whatever language you like, and that thing is going to behave like your big model, but you can see exactly how the decision is made because it's a concatenation of if then else statements. Symbolic regression is something very interesting, is a combination of nonlinear complex function that tries to fit an equation on the data, nonlinear equation, via genetic optimization algorithms. So it's kind of a brute force, but a little smarter. And you have a bunch of nonlinear functions, and this thing fits this nonlinear function with input parameters to generate the right outputs. And you can see what the formula does. That's what makes the decision for you. It's very fast to evaluate and very obvious. It's not a black box with a ton of weights and connections. There are other, you can do feature importance as well for with LIME or SHAP. We don't touch this, but also understanding what features have the highest impact. It's something good, and these methods are very well implemented in various libraries if you want to use them. Let me show you what I mean by the decision tree. Again, we are using the same problem. We have the thermometers, the source, we have this data set with this window of 20 time steps per each thermometer. We train a decision tree based on the output from the neural network. So our teacher is the neural network, non-Bayesian this time, just regular neural network with all weights the same. And the student is a decision tree. Once we have trained this, we print out the rules. The decision tree is just a bunch of rules. And this is what comes out. You say if sensor 0 at time 9 is less than 0.07, and sensor 1 at times 9 is minus or equal, it's less than equal than 0.30, and sensor 3 at times 9 is less than 0.08, and blah, 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 you get X 24, Y 24.44 and 23.50. Otherwise, if it's more than 0, this sensor 1 and T9, it will be 2782 and 2280, and so on. And you can see exactly how the values are out. This is very powerful because besides giving you the opportunity to code this directly into your C code or Fortran code or whatever you have, so you don't have to deal with that PyTorch crap. With adds, latency, and a bunch of things. This is just a bunch of if-then else statements. You know what's going on. You can fix this because if you know that these coordinates are wrong when one of this it's off, you can remove it. You can basically do a pruning yourself or automatic pruning to make sure that this is solid. So you can trust your model more and make sure that this is actually what you want. Of course, like everything in machine learning, you need parameters. In this case, parameters like the depth. This is a very long depth, or the split when you want to make sure that you make a decision at a certain point. But there are two parameters compared to several for bigger models. Let me show you the result for this particular case. So again, actual source thermometers. The cross that is kind of in mustard color is the student prediction, and the green X is the teacher prediction. So let's see how good they are. So you see that they start from the same spot. The mustard, the student is very staggering. It kind of goes a little bit in a stiff way because it's a decision tree. So you have if then else statements that makes it jump around. It's not very contiguous, but in the end, they go very close to the same place. And actually, I would argue that the student did a better job. So you see that distillation works, but now besides having good answers, we also know the reason that drive those answers. So this makes us trust the model a little bit more. Let me explain symbolic regression, and then we conclude and we can take questions. As I said before, symbolic regression aims to discover mathematical expressions that best fit a given data set, capturing both the nonlinear relationship between the variable. The expression derived by the symbolic regression are a combination of mathematical operators, such as the following: addition, subtraction, multiplication, divisions, transcendental functions, and power functions. So a bunch of nonlinear stuff. It's a sort of brute force. It uses genetic programming to do this. It's all automatic. My computer took 15 minutes to find these equations. And I split this search process into two coordinates. So two different models, one model for the X and one model for the Y, because smaller models, simpler models are more accurate. I could have gone for a model that does both, but this would have been much, much more complicated. So I just decided to split and make two models. And these are the formulas. So this may not make sense to you, but to me, this reveals something incredibly important. The window, the 20 times step window that I thought at the beginning that would give me more knowledge on how the heat is evolving and intuitively where the source it is, it's pointless. All this model tells me, and this is scientific discovery, like in this particular context for this particular problem, keeping track of the time step is absolutely irrelevant. What you need is the last reading. All this equation uses is x36, x38, x37, and x39, which are the four latest reading for each thermometer. For all the four thermometers, it's just the last one, is T0. All the rest, it's irrelevant. This is for X, and this is for Y. You see that there are no X0, X23, X1, because this model said, with just these four inputs, I can get away with a good result. This is fascinating to me. This is scientific discovery with this sort of AI. Let me show you. Again, same as before, mustard is the student, green is the teacher, and you see that just the student goes towards the source. The main model kind of goes around. They end up slightly in different places, but again, this model used the window, the 20 time step window. This uses just the latest reading, and the results are the same. Beautiful. So I understand now that I don't need the window. I saved a bunch of time by and storage by non-gathering those 20 time step at the beginning, but just the latest. So that simplifies my understanding and my model on how to get this right, just based on the data. So this is something that I really wanted to show you because it's fascinating to me. Conclusions. Uncertainty quantification is essential for trust and robustness with Bayesian neural network that allow us to basically do aleatoric and systemic uncertainty quantification. And this helps us understand where the problem might be with our model. Interpretability methods such as symbolic regression, decision tree, enhance model transparency and usability in HPC application because you actually know what your model is doing. While AI surrogates accelerate the simulations, model reliability, generalization, and explainability remain critical challenges. So everybody's talking about this is going to be great. We're going to go everything with AI, models completely replaced. We don't need that all dusty, crusty numerical methods. Well, wait a minute. Do you trust your model? In general, what I suggest you is that you use a simpler model. So the simpler, the better. Smaller, the better. So smaller model, simpler model allow you to get better results. So if you have a very complicated phenomenon, try to use multiple small and simple models instead of having a huge single complex model, because the accuracy will be much better when you concatenate simpler models and smaller models. The method presented here are not a must. There are new tools. They are new tools for model validation calibration, and it's just a way, one of the many ways to understand what the model is doing. There are other ways that I don't know, I don't understand, or they're too complicated for this sort of venue in terms of presentation in less than an hour. AI surrogate models are not just accelerators, but decision support tools, like I showed you. And it is important that we combine the efficiency of AI with the trustworthiness for real world employment. We are not deciding cats versus dogs. We are trying to solve scientific problems faster and better. So that's kind of my conclusion. These are a bunch of references are in the slide. You can check whatever you want. I use this PySR for symbolic regression. It's very simple to use. Very important stuff, apparently, and I'll take questions. Thank you.
Thanks, Alessandro. That was great.
Couple comments. That great presentation, amazing. Even if you do not follow every detail of what Alessandro's describing, I think the important takeaway is that we need to apply scientific methods here. It's not just saying, is this a bicycle in the crosswalk? That we have to apply these scientific methods. The details are not as critical as understanding that key point. And this is the future in the AI for science, is that we have to use a scientific method and all the tools that have been developed along the way. Not just randomly take what comes out of the model.
And this is just for surrogates. Of course, what I said before, it's all valid, and you are the judge on where it's good to apply certain things for AI. It can be even deciding a threshold, a parameter, and if that is gonna get your method, 10 times faster, because now you don't have to throw away a bunch of simulations, or who knows, you don't have to iterate as much with your solver. That's AI for science. It's an improvement given by AI, done very carefully and very precisely. It's a great example.
And I would actually like to walk this back into the current areas that AI is being used for. If you want to go from 80% correctness, that's a bicycle in the crosswalk, you need to apply this as well. It's just like if I use 2 bits, I can get 80% of the answer. To get those edge cases, you're going to have to do the same thing.
Yeah, I believe they don't do this. They have like decades. They've been done for decades. I think the problem that people don't want to deal with, the consequence of doing this sort of study, it's one, speed, because this takes longer, so you cannot do it as fast, not yet, at least. And the other thing is that people don't like reasoning in terms of probability. It's kind of hard. If I tell you that there is a 40% chance of rain, I still know that people don't exactly know what that means.
Yeah, they don't. But Alessandro, are they using any of these techniques in, is there a bicycle in the crosswalk? Is there a probability number coming out of that? Is there?
No. I mean, the probability number, it's not what this probability is about. The probability number, it's more like, it might be kind of a soft max where yes or no, or in this case, it's just a yes or no. So it's like 20% no, 80% yes. So that's a probability, but then it becomes 100% yes, because you need a yes or a no. You cannot have a probability and make a study. That's what I'm saying. So yes, sometimes you can see that as a probability, but what I'm showing here is not only a probability on the output, which is modeling again the aleatoric uncertainty of, is this a bike, but is the model that says, I don't know if this particular picture is, is actually 80% a bike, yes or no, or 20 yes or no. Because this bike may be upside down, it may be not a bike, it may be a motorcycle. So it's a different thing. This is kind of the extreme of uncertainty quantification. What is already there, it's some kind of randomness in the output that gets normalized by yes or no answers. So there is a probability, but it's not this probability. It's kind of a little more rough.
Right, and we don't. It's like in your car, it detects something up front and it slams on the brakes. So we have a yes, no. We don't have, well, I'm not quite sure, so I'm just going to slow down a little bit and read the data closer. So yeah, I think there's a lot of room for improvement all across the spectrum, but particularly in AI for science. I think these other existing uses will benefit from this down the road. Ashwin has a comment here. Talking of probabilities, we can improve upon mean and variance as you have shown. How do we check if a model can capture rare events and corner cases? Excellent question. Do we look for different metrics then?
No, it's the systemic uncertainty. That's part of the systemic uncertainty. Is basically imagine that each model weight. Let's just talk about the model weights now. Let's not talk about the aleatoric uncertainty. Let's assume it's perfect. You do the training on something that is very biased, on stuff that it's very, very, very common. And the input train that the certain weights in a certain way where you get this very narrow variance on the weight. So it's almost a scalar, very biased training set. And then in the input, you get this, basically you get this very rare event that I've never seen. Those weights will start freaking out. That basically the weight of the system, the weight of the model will start producing, you run the model 10 times with the same input, and you will see a high variance in the output automatically, thanks to that particular implementation on the weights, because the weights have never seen it. The variance that you see, it's the same example that I showed you with the training data. The training data with 10 and the training data with 50. That's exactly what it is that if you don't see certain cases, like a corner case, the model will notice if you model the model weights with random variables. It will show in the output. You need to run the model, the inference, 10 times, 30 times, instead of sampling from the output. So it takes time to do that, but that will show. That will tell you that that is a rare event. That's kind of what I showed you with the 10 versus 50 training set. That's exactly what it is. That's a good question, though. I'm glad that we reiterated on that.
Well, and then we can apply some of these techniques in Monte Carlo of smart sampling around those events, trying to get more data in those areas. Now, maybe we can't collect data from 100-year flood every day, but we can use smart sampling techniques that in many cases.
Yep. But you know at that point that you need to do that because you see it in the output. You will never know that, you know what I mean? Or if it's in production and a model gets an input that it's a rare event, you will see the red flags. In this case, with regular model, you don't see them.
So we're really arguing you don't need any weather stations in Kansas. They all need to be in Colorado.
One in Kansas, one in Nebraska, and many around the Front Range.
Yeah, this is actually one of the problems in weather and climate modeling is that the grid size is like a kilometer. It's like, how can you resolve mountains and coastlines and anything?
Even buildings now, Bob. There is the urban side of things that it's messing with the weather forecasting in the cities.
Okay, we have another question here. What about bootstrapping methods for finite sampling problems? Not sure I completely understand that question.
Me neither.
Maybe Maxim can explain that a little more. And another question, are you currently applying these techniques to interesting subjects? What applications already exist in production, and which one do you see emerging in coming years? I mean, this is we're really at the entry stage here. I mean, just beginning.
Yep.
Yeah.
I know that these techniques are used for non-invasive checks for rockets. Like the propellant inside a rocket needs to be very well uniform uniformly distributed inside the rocket. There is no there must be no bubbles, no little things. And I believe I read around that they use these Bayesian methods to make sure that what they are getting from non-invasive way of checking this by radiation, by ultrasounds, by things like that, actually have a certain quantification attached to it. And I think they're using some AI methods lately, but I don't have any references for that. I'm sure I'm not sure. I have seen talks about people claiming that their AI model can beat all the weather models currently around, and they're saying we validated this model by running it many times with many scenarios that we know, or hurricanes and stuff like that. And they say next we will do uncertainty quantification with Bayesian neural networks because it impacts the performance of the model, so it doesn't make it shine as much as they would like. So I'm sure people are thinking about this, but when they see the cost, that doesn't make it shine for getting grants or stuff like that, they kind of backtrack a little bit. So I am motivated to encourage AMD to actually invest more into creating hardware that facilitate this sort of approaches with probabilistic and sampling, something that it's a little bit more flexible than what we have right now.
Okay, Maxim is clarifying his questions. Bootstrapping is a classical resampling technique used to approximate the sampling distribution of a statistic by drawing repeated samples with replacement from the original data set.
I'm not aware of anything in this area. That might be something, but yeah, I'm not aware of that.
I'm not aware of that either, and Alessandro knows a lot more about this than I do, but we'll investigate that. That's a new concept for me at least. But smart sampling, I think, we're going to see a lot of that. Right now, it's brute force in a lot of the AI.
Okay, I hope I didn't give you a headache at the end of your day. And yeah, if you have questions or other things, please feel free to reach out to Giacomo and Bob. We'll always happy to chat.
Okay. Well, thank you, Alessandro.
Yep. Have a good day.
So I think we're done for the day. The system remains available for you to try any of the exercises or your own, as long as you're shared code that you don't mind putting on the system. We want to thank our presenters today. I think it was really nice as we progressively dug in deeper into the topics. Thank you all.
I would like to thank our AMD team for your time, for your support and great presentations. So this wrap up today. We are looking forward to seeing you tomorrow for our last day. And I wish you have a great rest of the day and see you tomorrow. Thank you very much.
Thank you,
Thanks, Sima.
Thank you, everyone.
See you
Bye.
tomorrow, everybody.
Thank you. See you tomorrow.
Bye-bye.